Audible? Hello? Hmm? Now? Audible now?
Yes, yes. So
Okay.
audible.
Thank you.
Hello.
Hello, good morning, ladies and gentlemen. A warm welcome to you all. I think it's time now that we can start the session. So, first of all, I welcome you. A very good morning to you all. Honorable Chief Patron Sir, Honorable Chief Guest, respected patrons, distinguished speakers from across the globe, my fellow participants, and dear students. It gives me immense pleasure to welcome you all to the inaugural session of the International Conference on Material Science and Applied Physics 2021, being organized by Department of Physics, Pachunga University College, Mizoram University. I extend my warm greetings to each and every participants of this conference who have joined us from different institutions from within and outside the country. Friends, as you are all aware of, material science has been in the forefront of recent advances in various fields such as nanotechnology, biomaterials, metallurgy, aviation industry, waste management, etc. Scientists and researchers have been working hard to develop novel, economic, as well as energy-efficient materials to fulfill the increasing need of humanity. Further, with the changing global climatic conditions, researchers have been compelled to look for efficient as well as eco-friendly materials. Friends, knowledge becomes valuable only when it is disseminated and applied to the benefit of humankind. The present conference has been visualized with an idea to create awareness among the participants on the recent advances in research works on material science being carried out in the scientific community across the globe. I hope this conference will go a long way in fulfilling this objective by providing a platform to gather and disseminate knowledge and know-how in diverse areas of material science. It is further envisaged that the academic discourse and discussions will result in future collaboration among the participants that will further enrich our knowledge and benefit humankind. I now take this opportunity to introduce some of the dignitaries who are present with us. First of all, I offer my sincere greetings to the Chief Patron of this conference, the Honorable Vice Chancellor of Mizoram University, Professor K.R.A. Sambasiva Rao. Sir, on behalf of the organizing committee, I thank you for accepting our request to be the Chief Patron of this conference. Sir, your vast academic and administrative experience and expertise has been the constant source of guidance to us. Though Sir is not present amongst us right now due to his other pressing schedule, I am sure his blessings and guidance will be always with us. Thank you, sir, for being there for us. Friends, it's my privilege now to introduce the chief guest of this conference, Dr. Sanjeev K. Varshney, Advisor and Head of International Cooperation Division, Department of Science and Technology, Government of India. Dr. Varshney joined DST in 1990 and has since worked in various capacities to facilitate bilateral scientific cooperation of India with partner countries. He has contributed a lot to the promotion of international scientific cooperation as well as scientific industrial cooperation. Presently, Sir Varshney is Indian co-chair, governing body of Indo-German Science and Technology Center, member in the Board of Directors, Global Innovation and Technology Alliance. Dr. Varshney is also member of the Governing Council of Indo-US Endowment Fund, International Advanced Research Center of Powder Metallurgy, and US-India Education Fund. Thank you, sir, for your kind consent to be a part of this conference as the chief guest. We are proud to have you in our midst. Friends, apart from our chief patron and chief guest, we have few other dignitaries with us who have constantly guided us with their valuable suggestions and encouragements. I now invite Dr. Lalshyat Jwala, the convener of the conference, to introduce the dignitaries for our benefit. So Dr. Lalshyat Jwala, please.
Mr. Chairman, sir, and the dignitaries and all participants from within and abroad. I once again welcome you to this first international conference on material science and applied physics. Today, it is a privilege to introduce some of the dignitaries, the patrons for this international conference who have guided us and encouraged us to organize this kind of event. First, I would like to introduce our Pro Vice Chancellor, Professor J.K. Patnaik. Pro Vice Chancellor Professor J.K. Patnaik is a Vice Chancellor of Mizoram University after assuming his office on 1st July 2020. And for some of the participants who are outside Mizoram, it will be an opportunity to talk a little about our institution as well. So Pachu University College is the only constituent college of Mizoram University, and we are administered under Mizoram University. Professor J.K. Patnaik served as professor in the Department of Political Science, Mizoram University from 2004. He is one of the senior-most professors in the university and has served as senior professor since 2014. He also took several administrative responsibilities, including head of department, dean, School of Social Sciences, chairman of Board of Studies, Committee on Acts, Statute, and Ordinances of the University, Executive Council member, Finance Committee, Academic Council, and governing body member of several educational institutions across Mizoram, among several other important responsibilities. Professor J.K. Patnaik completed his undergraduate and postgraduate education from Berhampur University, Odisha. He obtained his PhD degree from Queen's University, Kingston, Canada, in international relations and international trading regime. While he was a doctoral student, he was awarded Commonwealth Scholarship. Professor Patnaik has more than 35 years of teaching experience. He has contributed more than 45 research publications in reputed journals and books, and has delivered more than 80 invited lectures in national and international conferences. He has also organized several workshops, seminars, and refresher courses. He has guided 19 students for their PhD degree and 5 students for their MPhil degree. Thank you, sir, once again for being with us today and for your guidance for this conference. Our next patron is the principal of the college, Professor Aisal Thanzara, who joined the college in 2005 in the Department of Zoology. And he became a professor and principal of this institution from March 2021. He has a teaching experience of more than 15 years and actively involved in research. He received his PhD degree from Zoology, Department of Zoology, Mizoram University. And his research works includes the science of earthworm, animal ecology and diversity, and soil biodiversity. He has published more than 28 research articles, including one publication in Nature Science Journal on the title Global Distribution of Earthworm Diversity in the year 2019. He has completed 4 major research projects from UGC, DST, and DBT, and collaborative work with Department of Environment, Forest, and Climate Change, Government of Mizoram. He authored a book titled Popular Birds of Mizoram. He was a guest editor in one of the Scopus Index Journal, Journal of Environmental Biology. And he has been actively involved in several responsibilities, including member of Academic Council and Executive Council, Mizoram University, State Board for Wetland Conservation Project, State Board for Wildlife, and several others. Our principal is unfortunately not available today due to his official duty in Shillong, but he has conveyed his wishes for success of this event. Thank you, sir. The next patron is Professor R.K. Thapa, who is a retired professor from Mizoram University. He received his PhD degree from North Bengal University, Darjeeling. He joined Pachu University College as lecturer in 1978 and served in this institution till 2007. While serving in this very institution, he was also performing his duty as head of department in the then newly established Department of Physics, Mizoram University from 2005, which he eventually joined in 2007. And from there, he retired as a professor in 2017. During his service of 40 years as a teacher in the college and the university, he was entrusted with several important responsibilities, such as head of department, dean school of physical sciences, proctor of the university, executive council member, court member of the university, among many other responsibilities. Professor R.K. Thapa works on theoretical condensed matter physics, particularly in the field of photo emission, electronic band structure, optical, thermoelectric, and magnetic properties of half metals and semiconductors. He has contributed more than 250 research publications in journals and completed 9 research projects. He is a reviewer in 19 Scopus Index journals. He has successfully guided 21 PhD students. He also examined more than 50 PhD thesis work of PhD candidates from various other institutions. During his service, he was actively involved in research collaborations with Dr. Arthur Arns from Max Planck Institute for Microstructure Physics, Germany, Professor T.P. Sinha from Bose Institute, Professor A.H. Reshak from Bohemia University, Czechoslovakia, and several other institutions within India and abroad. He was a visiting fellow of Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, INSA fellow in Daransbury Laboratory, Cheshire, US, UK, Max Planck Institute, Germany, and Wrocław University, Poland. During his service, he was awarded Best Science Teacher by Mizoram Legislative Assembly way back in 1986. Eminent Physicist Award by Physics Academy of the Northeast India, Honorary Director, Chair Professor, and Emeritus Professor by Condensed Matter Physics Research Center, Nepal. Thank you, sir, for your constant encouragement and guidance. The last patron which I am honored to introduce in this conference is Professor Tankeshwar Kumar, who is currently serving as Vice Chancellor of the Central University of Haryana. Earlier, he has been Vice Chancellor of Guru Jambeswar University of Science and Technology. He served for about 5 years and 9 months. Prior to joining as Vice Chancellor, he was serving as UGC Professor of Physics and Director of Abdul Kalam Computer Center at Punjab University, Chandigarh. He also has taken additional charge as Vice Chancellor of Deen Bandhu Chotu Ram University of Science and Technology and Chowdhury Bansilal University, Bhiwani. Professor Tankeshwar has 35 years of teaching and research experience. He has contributed more than 165 research papers in journals of international and national repute, with more than 1,400 international citations. His H index is 22 and I10 index is 40. His research area is theoretical and computational condensed matter physics and nanotechnology. He is the first UGC professor in India in FRP. He has guided 13 students for their PhD degree. He is fellow of International Academy of Physical Sciences and member of National Academy of Sciences, Allahabad. He is editorial board member of the international journal World Condensed Matter Physics. He has been member of Senate and Syndicate of Punjab University. He has been member of various committees at state and national level like UGC Examination Reform Committee, Chairman Committee to establish First Skill University of Haryana, Planning Board, YMCA University of Science and Technology, Faridabad, Academy, ASC of J.C. Bose University of Science and Technology, YMCA, member, Board of Governors, IIIT, Sonipat, Chairman, Committee for Students Election in Haryana, Chairman and member of NAP, peer teams from time to time, and search committees for selection of vice chancellors. He has been awarded Associateship of ICTP Italy. He has been research leader ICTP Italy between July 1993 to August 1993. He has visited abroad 17 times to Europe, Africa, and America. He has been awarded with Golden AIM Most Dedicated Vice Chancellor Award 2020, Vidya Sagar Award 2017. Thank you, sir, for guiding us and for encouraging us for successful conduct of this conference. Thank you.
Thank you, Dr. Lakshya Jwala, the convener of this conference. Friends, after the introduction of the dignitaries, so I would like, on behalf of the organizing committee, I would like to invite our patron and respected Pro Vice Chancellor of Mizoram University, Professor J.K. Patnaik, sir, to deliver the inaugural address. Professor J.K. Patnaik, sir, may kindly deliver the inaugural address. J.K. Patnaik, sir, please. I invite our respected Pro Vice Chancellor, Professor J.K. Patnaik, to deliver the inaugural address. Sir.
Am I audible?
Yes, sir. Yes, sir.
Okay, there was some disruption in the middle. Anyway, thank you, Chairman, sir. Respected Chairman, my colleague, Shah Juala, I don't know who are the people present. I think Professor Thapa is present, right? Professor Thapa, my old colleague, and the Vice Chancellor, Professor Ankeshwar Kumar, Central University of Haryana, and other gentlemen are not present, right? So, in absentia, I would like to, address our Vice Chancellor, Professor K.R. Sambasivarao, and the Honorable Chief Guest, Dr. Sanjeev K. Varsni, and other panelists, as well as the participants of this international conference on material sciences and applied physics. Actually, I am very happy and feel privileged because of the absence of my Vice Chancellor. I've been given the onerous task of giving the inaugural address, delivering the inaugural address. We are really privileged I'm in fact privileged because Pachunga University College, which the convener introduced as a constituent college of Mizoram University, rightly so though, we consider Pachunga University College as another campus of our university, and we often call Pachunga campus of Mizoram University because Pachunga University has been, one of the important institutions in the state of Mizoram, one of the oldest institutions in the state of Mizoram. I think the oldest, if I'm not wrong. And we would like to always identify ourselves, being the university though, would like to identify with Pachunga University College as our own institution. And in fact, it is our institution, and that's why we generally identify it as the campus of Mizoram University. Regarding this conference, actually, I am not at all, I'm rather a cipher in the field. I have no idea at all about material sciences or even applied physics. And whatever little understanding that I have got, had from my older brother, who was a physicist, solid state physicist, who did his PhD. Of course, he died a few years back. He did his PhD in Moscow State University in physics and mathematics under this Government of India Fellowship. And he would be always talking about physics. And according to whatever little understanding that I got, is that physics is the science of matter, and that everybody does know. But in every aspect of our day-to-day dealings, we confront ourselves with physics. Physics is part and parcel of our day-to-day life, although it is a material science. But when you talk about material science, it's definitely an amalgam of solid state physics, metallurgy, and chemistry. And the basic understanding of the origin of properties and materials, particularly, will help us in understanding the dynamic process of various metals, and also it will help us in understanding pursuing rather engineering, electronics engineering, or information processing, or even nuclear power. All these things I do not know much, so I don't want to talk about. I don't know anything rather. I don't want to talk about the subject, but I would like to say that by having this kind of conference, Pachanga University is taking the lead not only in Mizoram but also in Northeast India. Reason is that there are very few institutions, even Northeastern University also is one of the important institutions in the region. Very few institutions have got so much of activity at the undergraduate level. Pachanga University College is an undergraduate college. Now, of course, we have got a few postgraduate programs and not many basic sciences. But what is more important for us is that it is a matter of pride, rather, that Pachanga University College is able to, rope in so many people from across different parts of the country as well as outside. I'm given to understand by the convener that we have got also many foreign delegates who would be taking part in this conference. This is possible, and this has been possible because of the advantage of the pandemic. See, pandemic had brought in so many disadvantages and so many bad things for us, but there are certain things which have been, quite a blessing in disguise, in the sense that we have been able to talk to people, we engage in conversation, we discuss about the academic matters from across the globe. And a forum like this, wherein our teachers, our students, our researchers would get exposure through the interactions and conversations that we would have today. And for this, I would rather congratulate the faculty of physics, Pachanga University College, as well as the patrons, and of course it included me, and the other distinguished people who have been contributing for materializing this kind of material sciences of conference. So I am very much happy and delighted to be part of this conference by having delivered the inaugural address. I do not want to waste my time or your time by speaking something irrelevant to the theme that we are going to deliberate, and I expect that the deliberations will be quite productive and helpful for solving some of the problems that we might be confronting in the course of your research. And also, I would also expect that it would benefit our students who have been, pursuing their research, or who have been pursuing even the postgraduate or undergraduate programs in physics. They should also be encouraged to be part of this conference so that they would benefit out of it. So again, I congratulate the organizing committee. I congratulate because I have got a soft corner for Harshad Jala, and I have been always telling him that he is a very good teacher. And in fact, I should not share this, but I always said, why don't you come to Mizoram University? Why don't you join Mizoram University rather than sitting in undergraduate college in Pachua? Then he said, sir, I can do so many things. So my personal congratulations to Harshad Jwala and to all the people who are engaged in organizing and in conducting this conference. So my best wishes to all of you, and I hope it will be a productive conversation amongst yourselves. Thank you very much. Thanks a lot. Thanks.
Thank you, Pro Vice Chancellor, sir. Thank you for your encouraging words. Even though being a man of humanity, you have always supported the steps taken by the science department and science faculties. Thank you for being part of this conference. I take this opportunity now to invite Professor P.K. Patra from Department of Physics, Northeastern Hill University, Shillong. Professor Patra was a faculty of this department for a brief period before he went back to NEHU. So I would be very happy to have him share his views on this conference and in general about the physics. Professor Patra, sir, please. Friends, I'm sorry, Professor Patra is having problem with a connection issue. So I think we'll now invite the co-convener of this conference, Dr. Suraj Kumar Singh, to deliver vote of thanks. Dr. Suraj, please.
A very good morning to all. It's a great honor for me to offer a vote of thanks on behalf of Icmsap 2021. At the very first, we would like to thank our honorable and respected patron, Professor K.R.S. Sambasiva Rao, DC Mizoram University. We would also like to thank Dr. Sanjeev Kumar Bharsne, advisor and the head International Cooperation Division, DSD, Government of India, who accepted our invitation to serve as chief guest and deliver a plenary talk despite his busy schedule. He is not with us right now in this inaugural function, but he will be giving a plenary talk tomorrow morning. We are eager to hear him, sir. We thank all the patrons, Professor J.K. Patnaik, to VC Mizoram University, our dynamic principal, Professor Lantanjara, retired Professor R.K. Thappa, and Honorable VC Central University of Haryana, Professor Tankeshwar Kumar, for their gracious time. We have been fortunate to have a renowned distinguished professor in physics and editor of Journal of Physics and Chemistry of Solids, Xavier, Professor Arun Bansal from Northeastern University, Boston, USA. We welcome you, sir. We shower our hearty gratitude to all the speakers for their precious time and agreeing to share their knowledge with us. And we thank all the advisory committee members for their valuable contributions in their own way. We should not forget to thank a very good friend of our convener, Professor Bahadur Singh from TIFR, who invited me for his kind help, starting from arranging the resource person, making timetable, and many other technical things. We thank all the department colleagues and associates for their encouragement and support. Last but not least, I'm thankful to all the participants. Without them, this conference would not be a vibrant event. I also want all the participants to have an effective interaction with our resource persons, especially for those young and new scholars who are yet to start their research career, and for those who are still confused about their PhD topic and the choosing guide. The list of the speakers have been uploaded along with their title of the talk and email ID in the WhatsApp group. You can discuss your programs with them in and of the conference. With these words, I conclude my vote of thanks. Thank you. Have a wonderful day. God bless all.
Thank you, Dr. Suraj. Friends, I am very happy to inform you that Professor Tankeshwar Kumar, Vice Chancellor of Central University of Haryana, is with us, presently with us, and it would be our pleasure to hear from him. So I request Professor Tankeshwar Kumar to address the gathering with his views on physics in general and material science in particular. So Professor Tankeshwar Kumar, please, sir.
Professor Tankeshwar Kumar will be joining in a couple of minutes.
Okay, thank you, ma'am.
Right.
All the participants are requested to wait for a while because Professor Kumar, as I know, is very, very busy person with responsibilities as a Vice Chancellor of his own universities and other activities. So I hope he will be able to join us soon.
Is there any password?
No, no, madam, no password.
Okay.
Yeah. So I hope we'll be able to hear from him soon. So let us wait for Professor Tankeshwar Kumar.
He has joined, I think. He has joined. Yes, he has joined. You can again invite him.
Yeah, I invite Professor Tankeshwar Kumar, Vice Chancellor of Central University of Haryana, to address the gathering with his views. So Professor Tankeshwar Kumar, please.
Thank you, Shivraj. Thank you very much.
Welcome, sir.
Yeah, it is a really great that you are organizing a conference on material sciences and applied physics, right? And it's a really matter of pride for us because when we see that our students are contributing to the field, right? That is very important. And then, to the real kind of thing what you really country is looking for. And, the material science is a very, very important aspect of any, I say any science, right? So because if we look at the things, how the things are progressing, right, the way we are progressing, it all depends upon the what kind of the material we are having, right? If we just look at the simple science, the science was available but the material was not available, right? Because if you just look at, we have the wheels. If we look at the wheels, we have the wheels for many, many years, many 100 years, but we could not put a wheel to everything. We could not put a wheel to everything. Well, for example, I'm sitting on a chair. I could not put the wheel maybe 30 years back. I could not put a wheel to my suitcase maybe 30 years back, right? But now I can put everything in the wheel and still we are moving, because it is because we have the different kind of the material we required, and that is now we are able to do it. And we are now talking through this mode, and that is happening because we have better materials. We have the better material in terms of, where by which we could improve our speed of the speed of the connectivity as well as the speed of processing. That is a, we could improve because we could have the better material. Right? So the importance of the material is very important, and it is not that we should create the material by doing the research, right? That should not be the job of the I will say the physicist. Physicist's job is not only to see that, okay, that if we generate this kind of the material, we will have better flexibility in terms of, let's say, in the electronics are, today we are considering that how we can have a flexible material where, we can bend the materials and still we can have the same properties of the material so that we can have the flexible electronics, right? So that means we are now looking for the 2D electronic materials and things like that, right? So that is the way, we are doing, and we are doing the good research. So what I mean is the research is not everything, right? Research is not everything, because if I look at the research in material science in India, we have a very good contribution. We have very good contribution, but but if you look at the industry linkage to the material sciences in India, it is, I will consider not up to the mark at least. It may be failure, but it is not up to the mark at least, because we are not producing ICs, we are not producing semiconductors, whatever you call it, right? So we have to still work on such things, and I think it is now duty of our material scientists that we should go for. It is not easy to say that we can go for the startups and things like that, because these industries are very large scale industries, and so. But anyway, we are here. We are as a scientist. We have to convince that, okay, that if we go for the industry linkage of the material sciences, and really there we can only then this country can be a developed country, right? So that is the way we should guide to our governments, and I hope that some points will be taken care by your this experts in this conference, and I really congratulate to you for organizing this wonderful conference, and I believe that this conference will result in you know, this conference will result in some useful output in terms of what we look at as our country to be self-reliant, and we are our country is looking for the development in the defense in the defense field, and where we want to really produce the things, and that is where we're looking for is in terms of the manufacturing and the production. And that is the way I see that our scientists now should look towards their research in terms of the output of the research. We are talking about the learning outcome of our education, but we are also looking for the outcome of our research also in terms of the manufacturing within the country. So with these words, I once again congratulate you and Mizoram University and for organizing this conference. Thank you very much. Thank you. Jai Hind, Jai Bharat.
Thank you so much, sir, to hear from you. We are really proud to have you in our midst. So I hope this conference will try to delve into some of the points that you have put forward. So, dear friends, with this, we'll move into the second part of our inaugural session, in which we have a keynote address. So it's my privilege now to invite Dr. Mahesh Kumar, Department of Electrical Engineering, IIT Jodhpur, for the keynote address. Dr. Kumar, he obtained his MTech degree in solid-state material from IIT Delhi and PhD in engineering from Indian Institute of Sciences, Bangalore. Dr. Kumar has a checkered career and is the recipient of Icmsap Medal for Young Scientists for the year 2014, MRSI Medal 2016 from Material Research Society of India, DAE Young Achievers Award 2016 by BRNS, and Research Excellence Award 2020 by IIT Jodhpur. He has been recipient of many fellowships like Bhaskara Advanced Solar Energy Fellowship 2018 to work at South Dakota State University, USA. Fulbright Nehru Fellowship 2021 to work at MIT, USA. The Royal Society International Exchange Award 2021 to work at University of Edinburgh, UK. Dr. Kumar has published more than 130 research articles, and his research interests are focused on two-dimensional materials, nanomaterials, sensors, semiconductors, and devices. It's my proud privilege to invite Dr. Mahesh Kumar to deliver the keynote address on the growth and gas sensing properties of 2D materials. Dr. Kumar, please, the stage is yours.
Inaugural function is keynote speech
I'm very sorry to inform that there was a slight misunderstanding in the program schedule. So I'm sorry to inform you that the keynote address is supposed to start at 11. So with this views We have heard from our dignitaries, from Professor J.K. Patnaik and Professor Tankeshwar Kumar, and introduction of our dignitaries. We have come to the end of the inaugural session. So we'll start the technical session after a break of say around 5 minutes at 11 with Dr. Mahesh Kumar for his keynote address. I'm sorry for the what you call um, the mishap that was because of the misunderstanding in the program that occurred. So once again, friends will meet after a break of not a break, I think after about 5 minutes when we will hear from Professor Dr. Mahesh Kumar. I thank you all for joining the inaugural session and looking forward to your participation in the upcoming technical sessions. Thank you all.
lấy sắc sắc về cho thải này nào March
Welcome back, friends. So we'll start the technical session with a keynote address. The keynote address is scheduled for a duration of 1 hour with the talk of 50 minutes, followed by a short discussion of 10 minutes. For this session, the keynote speaker is Dr. Mahesh Kumar from Department of Electrical Engineering, IIT Jodhpur. Dr. Mahesh Kumar did his MTech degree in solid-state physics, solid-state materials from IIT Delhi, and PhD degree in engineering from IISc Bangalore. Dr. Kumar had a checkered career and is the recipient of Icmsap Medal for Young Scientists for the year 2014, MRSI Medal 2016 from Material Research Society of India, DAE Young Achievers Award 2016, and Research Excellence Award 2020 by IIT Jodhpur. He has been the recipient of many fellowships, such as Vaskara Advanced Solar Energy Fellowship 2018 to work at South Dakota State University, USA, Fulbright Nehru Fellowship 2021 to work at MIT, USA, the Royal Society International Exchange Award 2021 to work at University of Edinburgh, UK. Dr. Kumar has published more than 130 research articles, and his research interests are focused on two-dimensional materials, nanomaterials, sensors, semiconductors, and devices. May I now invite Dr. Mahesh Kumar to deliver the keynote address on growth and gas sensing properties of 2D materials. Dr. Mahesh Kumar, please.
Yeah, thank you, Professor Sivaraj. Just a minute, I will share my slides. Can you stop this one sharing? Yeah, thank you. Yeah, can you see my slides?
Yes, yes, we can see.
Yeah, thank you. Yeah, thank you so much. This one. So very good morning to all the viewers. This one. And today I'm going to talk about the 2D materials, how we can grow the different type of the nanostructures by using the chemical vapor deposition, and we can use for the different applications. And mainly I'm going to talk about the their gas sensing applications. So at IIT Jodhpur, my research group is, just a minute. Yes, yeah, thank you. So at IIT Jodhpur, we are working on the 2D materials and metal oxides. So mainly we are working on the material synthesis, device fabrication, and their application for sensing applications. For example, gas sensors. Also, we are working on the heavy metal ion sensors and this photo detection applications. And today this one talk is focused on the 2D materials, mainly for this one gas sensing applications, how we can use these 2D materials for the gas sensing application. This is the outline of my talk here. First, I'm going to talk about the growth of MOS2 by chemical vapor deposition and how we can grow this one different structures. For example, horizontally aligned this one MOS2 flex or vertically aligned MOS2 flex, and how these basically their orientation is affecting the gas sensing applications. We have also fabricated room temperature gas sensors, because you know this mostly these gas sensors, they are working at the higher temperature, and maintaining always that temperature is a challenge, this one. So if we can fabricate this one the room temperature, that can this one solve the power problems. Also we can make this one here, we can save the energy. So what we have done here, we have used the photo activation. So we have used this gallium nitride based LED and made the hybrid system, and then we have prepared this sensor particularly based on the 2D materials. Also, I am going to discuss about this one MOS2 functionalized with RGO particle for efficient this one room temperature NO2 sensors. So generally in the semiconductor devices, defects are not this one preferable, but in gas sensors we can create basically these defects, and then we can improve their sensitivity and selectivity. Also, I will talk about the 2D, this one SNS2, that is the new material here. Again, 2D materials. We have synthesized this material and made again the gas sensors. If we talk about why we need the gas sensors, so main application of these gas sensors is in the air pollution, and around per year, around 8 million deaths per year is due to this one household or this one outdoor air pollutions as per WHO reports here. And if we see this one pollutants in the air pollution, these are the three main basically this one pollution elements. One is the carbon, this one monoxide or dioxide, another one is the nitrogen oxides, and third one is the sulfur, this one dioxide. And today I am going to talk about this one, how to detect the nitrogen, this one oxides here. There are secondary this one pollution elements, but they are in this one less quantity, also depending on the industry or pollution, in which area pollution is very high. So we can also make this one VOC sensors and particularly these gases sensors. But today I am going to talk about how to detect the nitrogen oxides here. If we see the main this one source of nitrogen oxides is our this one petrol or diesel engine is there. So at the high temperature, this one nitrogen and oxygen both are combining and making this one nitrogen oxides. There are other this one source, forest fire or basically thunderstorms, but we don't have control on these two. This one only we can control only this one from the vehicle pollution, how much pollution is there. So first thing, how to monitor this one, my vehicle is there, how much pollution basically, how much pollution emission is there from this one. Another why we have to detect this one. So first thing, NO2 is toxic in high concentration, and can create this one different type of the disease here. Another, when nitrogen basically this NO2 mix with the oxygen, this will make the smoke and reduce the visibility. Mainly in the Delhi in the winter, we can see under the light when your oxygen and NO2 both they are mixing is making the smoke here, and because of this one visibility is less. Third one, when nitrogen oxide mixed with the water vapors here, they create the acid rains, and because of the acid rain, they can destroy basically metal structures, even stone also. And we know that this one Taj Mahal, this color is changing because of the acid rains, and now the government they have stopped the industry nearby these areas. So basically we can control the pollution. Another, again, this acid rain is there, this one may change, particularly the pH level of this one, our water resources are there. So here first thing we have to detect this one, how much pollution is there, and second, this one we have to control on the emission here. So today I am going to talk about this one, how to detect here. So you can see from this one how much this one pollution is there from the vehicles, and particularly in this video, if you see this vehicle, mainly they are basically this vehicle is there. They are detecting particularly this one giving the air pollution certificate, how much pollution is there, but they have never tested this one, how much pollution is there from their vehicle. That we can make out this one. But if we can make some small sensors here, and that similar to GPS is there. Now suppose whenever we are going somewhere, we can see in the GPS how to go this one. So similarly, if we can develop a small chip here, and by using this chip here, if we can connect basically these vehicles, then through RTO, and then whenever this emission level is high, this one from the old vehicles, we can stop and we can control, basically we can control this emission. Another, this one now in these cars here, particularly in these cars, basically in the higher cars, this one take the this air from outside here. So how to decide this one? Okay, so we can mount these pollution sensors outside, and these cars will suck the outside air when the pollution is less. Otherwise, they will not basically suck from the outside. So we can these we can use in the hybrid ventilations here. We can mount outside the cars this one, and only this air circulation will take place this one whenever the pollution is less this one outside the car here. So next, how to make these compact this one sensors, because there are the different physical or chemical phenomena that we can use to make these detectors. But whenever we are making any sensor, these are the basic characteristic of any sensor to develop this one. First thing, we have to see how much sensitivity is there here. Sensitivity means when our concentration is changing this one, how much change is there in the output, that we want the high change. So we can measure even this one small change is there in the input quantity. So that we call the transfer function here. So transfer function is linear, non-linear, that is also matter. So here we check the sensitivity, stability with temperature, fast response should be there, room temperature, operability, this one. So these are the basic, this one here, basic parameters. Again, of course, the how much power consumption is there, how much cost is there, reliable is there here. For example, we are using this one different, this one mobiles, your iPhone is there, and another this one, another phone is there, because in iPhone, your sensors, your touch screen is very good. That's why their cost is very high is there. So these are the basic parameters for the sensors here. By using this one, we can basically, we can make this one different type of the this one sensors, low cost. We can develop these low cost sensors here. So now here, how to make the NO2 sensors. So first, basically this chemical based, or you can say the resistance base here. This was developed in 1960 by the Taguchi here, the one Japanese, this one scientist here. And after this one, different metal oxides were used to make the different type of the sensors, including the NO2. We can use the zinc oxide, TiO2, WO3, and tin oxides. So we can use in the bulk form. Here we can use the nichrome heater, and then here we can deposit this one bulk material, or we can deposit the thin film. So when we are using the thin film, basically in that case the surface area is there, that we can, this one material we can reduce, and surface area we can increase. Another we can use here this one, our nanostructures. In the nanostructures, we know the aspect ratio is very high. So when aspect ratio is high, this one, because this one is the chemical adsorption is there. So on the surface here, your charge transfer is taking place here. So when on the surface charge transfer is taking place, here we can use basically nanostructures, and then we can improve their sensitivity. But these metal oxide based semiconductor, they have some drawback. One is their sensitivity is low. Another one is the selectivity is poor. And here, for example, zinc oxide or other these metal oxide, they are also depending on the environmental factors. For example, humidity, because in the different region of the country, humidity is different. So when humidity is different here, what is happening? Their properties are also changing here. Another drawback is that one is the operating temperature. When we are using the bulk, this one, operating temperature should be more than 250 degrees centigrade, or generally in the nano, this one is the 150 degrees centigrade is there. So that one is the another drawback is there. So again, this your heating, that one is related with the power consumption. So in these devices, power consumption is high. So briefly, I am going to talk about this one here, how these gas sensors are working, mainly for the students, this one here, how particularly these gas sensors are working. So you know this one p-type and n-type semiconductor. So in p-type, your Fermi level is close to the valence band. In n-type, Fermi level is close to this one, your conduction band and valence band. Now, if we join both semiconductors, what will happen this one? At t equal to 0, in this region we have the hole, here we have the electron. Now when we are joining, because of this carrier, this one concentration gradient, electrons will move from n-type to p-type, holes will move from p-type to n-type here. And when they are moving, basically, they are leaving this one immobile ions here. So these ions, these are immobile, because from here your holes moved in this direction, electron moved in this direction, because here carrier concentration is not equal. Here electron concentration is high, here holes concentration is high. Because of this one here, now electrons and holes will move from one side to the another side, and after some time we will get the steady state here. And in this case, we will get the electric field is in this direction, and now this electric field will not allow further this one diffusion of holes from p to n and electrons from n to p, and so we will get this one stable state here. Now in this case, what is happening in this basically region, we don't have the free this one your electrons or holes, we have only ions. In this case we have the ions, and generally in the p-n junction we can make this one electrode here and another electrode is here, and then we can measure basically how much this one how is your current voltage characteristic is there. So in the forward bias, current is high, in the reverse bias, current is low. So we can use to explain these gas sensors here working principle, we can use the same concept and then we can explain. Suppose I take this one n-type semiconductor, and if I take the contact one from top, one from the bottom, now how much will be the resistance? Resistance is depending how much between the electrode here, how much this one your length is there between the electrode, how much is the basically here electrode area is there. So simply we can calculate this resistance is R equal to rho L upon A. And now here your resistivity is depending on the here concentration, how much concentration is there. And suppose we are not changing this concentration, this one is the constant is there. Now this one, when we measure the resistance, this semiconductor materials resistance will be constant. Now if we take another situation, If I bring hypothetically some p-type semiconductor near to this one, what will happen? Because of this one concentration gradient, here one depletion region will form. So this depletion region will form here. So now these electrons will diffuse in this side, holes will diffuse in this side. And now if I measure the here resistance, how much will be there? Resistance will change because we don't have the free carriers in this region. And now the cross section area is decreased because carriers can move only in this direction, not from here to here. This one, electrons cannot move this one. So now our area will be the A minus del A. So cross section area is decreased. When cross section area is decreased, now the resistance is that this will increase here. So now resistance will increase. So there is a change basically in the resistance when we are bringing this one p-type semiconductor near to the n-type semiconductor. Similarly, here we can assume this one, this gas molecule is the p-type semiconductor. That means gas molecule is taking the electron. What p-type semiconductor is doing here is taking electron from n-type semiconductor. And suppose this one semiconductor, gas sensing semiconductor is n-type, and now gas molecule is this one taking the electron. Concept is same. That means here semiconductor materials resistance will change here. So when the resistance will change here, we can measure this one, how much concentration of this particular gas is there. So when more number of this one gas molecules are coming, they will take more number of electrons here from the semiconductor, and because of this one, this resistance of this semiconductor material will change here. So based on this concept, we can fabricate this one, we can make the gas sensors, we can explain these gas sensors, properties, how these gas sensors are working. So now why 2D materials? That one is in the metal oxide, any semiconductor materials. If you take this one, concept is same. But why 2D materials for the gas sensing applications? So now the general concept is there here. When we reduce the dimension, what we are doing in the 2D materials, we are reducing their dimension. For example, your graphene is only one thin layer is there. If you take the carbon, basically, in that case, here your thick material is there. So in the 2D materials, what we are doing, we are reducing their dimension. Now, when we are reducing the dimension, what will happen? In classical or general concept is that when we reduce the dimension, confinements make mobility low. That's why these terminals we are putting in the gels, because we are reducing their mobility here. So same this one concept, this one for the classical system, when we reduce this one, mobility is low. But here electronic concept is totally different. When we are reducing this one, their dimension, because of the quantum confinement, their mobility is high. And best example is the graphene here. If you take the bulk carbon, mobility is low. When we are using the graphene, basically mobility is high here. So we can use basically these 2D materials for the gas sensors. And when mobility is high, that means that device speed will be high. So we are expecting in 2D materials, our gas sensing response is that would be higher than this one bulk materials. So this one is the one advantage when we are using the 2D materials. So we can expect their high gas sensing response. Another, this one advantage, this one is the one device speed is higher. We can understand this one. Suppose this one is the bulk material. Okay, bulk material, we have the different layers, many layers we have this one unit cells. And now suppose one gas sensing atom is coming near to this one. What will happen? This atom impact will be only on the top layer, here maximum impact, some impact will be on the bottom layer. But carriers can move from this side. Okay, so overall the change is there, so because now carriers, they have to move the longer, some change will be there. Because of this change here, we get the change in our current or the resistance, whatever we are measuring this one. But as compared to the 2D materials, if we compare with the 2D materials, in the 2D materials, we have only few monolayers, and now the impact is high. Suppose here, this sensing, this molecule is there. If this one is stopping this one, overall this one change is there, that will be the high as compared to the bulk, because in the bulk we are changing only the path, but here we are stopping the complete basically conduction when we are having the few monolayers. So other thing, because this change is related with the sensitivity, so our sensing response will be higher in 2D materials as compared to the bulk materials. So this one is the another advantage is there. If you see in the literature here, this one, this one basically Cambridge group is there. They have used this one graphene for the gas sensing applications. Here you can go through this paper, and what they have done, this one, they got a very good sensing response. But drawback is that one is this sensor is not selective here, because this one is sensing S2, NO2, this one NS3. So one drawback is that here graphene based sensors, they are not selective. Another one is that this recovery is not complete here. Because that means we cannot use for multiple times, because we have to wait for the longer time to bring this one sensor in the back to the initial condition here. So that one is the another drawback is there in graphene based sensors. So we thought, can we use this one now, this 2D materials, MOS2, that one is having the band gap here, because graphene does not have the band gap. These are the basic properties. This one here, these MOS2, they exist in the two phases. One is the 2H phase, this one is the semiconducting phase, this one is the metallic here. And now, because for the gas sensing applications here, 2H phase is there. This one is the semiconducting phase, and this one is more favorable. Why more favorable? Because 1T is the metallic. Metallic means we have large number of electrons, and in semiconducting we have less number of electrons. So when we are taking or giving basically in the large number of electrons, that change is the small as compared to the semiconducting materials. So this one is similar. For example, this one, we can take, for example, Ambani. If he is giving the 5 crore rupees, his lifestyle will not change, because he has the this one higher, his total property is very high. But one poor people who will get the 5 crore, his lifestyle will change. Similarly, in the this one metals, because electron concentration is very high, they are losing or gaining some little bit concentration. Their overall this one carrier concentration will not change, but in semiconductors will change. So for the gas sensing applications, our preferable basically material is there. That one is the semiconducting phase is there. Band gap, again, because here we are not studying this one depending on the number of monolayers, and we can characterize after the growth from the E2G and A1G peak how much gap is there. We can calculate how many monolayers we have grown. So how to grow these MOS2 layers? So if you buy, for example, from the market 100 gram of MOS2, the cost is around 5,000 rupees on the Sigma Eldridge here. But if you buy this one monolayer around 1 centimeter by 1 centimeter square, MOS2 monolayers on MTI, this cost is the around 50,000. Okay, so you can see this one, how much this one difference is there. Here we are getting 100 gram, here we are getting only one monolayer. And roughly, if you can convert all these 100 gram MOS2, this one bulk MOS2 into the single monolayers, here this one your total cost will be this one around 1 million rupees. So how to make this one from 5,000 to 1 million rupees? Basically, just we have to separate all these layers, this one bulk materials, into the monolayers. That means here the growth method is there. That is not easy. Otherwise, anyone can do this one. So that one is the complicated of synthesizing these materials. And what we have done at IIT Jodhpur, we have used this one chemical vapor deposition. We have 3 zones this chemical vapor deposition system. So in one zone we are using the sulfur, another we are using the MOO3 for this one, and here we are using the sample here at different places. We use this one and optimize this one, and carrier gas we are using this one argon we have used. So argon basically here sulfur is evaporated, and now argon basically is pushing this sulfur to move in the second zone, and now here your chemical reaction is taking place, and MOO3 and sulfur both are reacting and making the MOS2 here. We have grown the different basically structures by this one playing with these deposition parameters, and these are the optimized parameters. Suppose we want to grow the horizontally aligned, this one MOS2, this one is the vertically aligned. So in the vertically aligned, one thing we have to keep the temperature high and flow high. So in that case, these molecules basically, they are not getting sufficient time to align this one to grow on the horizontally. And in this case, this growth will start the vertically aligned, particularly in this one. So we create the high flow, and high flow is this one creating help to grow the vertically aligned here. So we have grown both vertically aligned and this one horizontally aligned, both this one also depending on the positions here. So you can see these are the very nice flakes. These are the horizontally aligned here, and this one is the vertically aligned flakes here. And we have characterized this one because MO3 is converted into MOS2 or not, this one, so that we can do that by XRD we can see, and by we can see the Raman spectroscopy, and we got basically in the vertically aligned this one, here this peak is higher, but in this case is almost this one, this intensity is less. So from this one we can also see here, from Raman spectroscopy also we can get the rough idea how is our surface morphology is there. Is this one is the horizontally aligned or vertically aligned is there. So we have grown these different, this one horizontally aligned and vertically aligned. Now, what is the impact of this alignment on the gas sensing properties? So then we have made this one sensors. So we have deposited chrome gold, this one around 10 nanometer chrome, and then 200 nanometer gold, and the gap is there between this one both electrodes is around 100 micron. We have taken around 100 micron, and this one is the horizontally aligned and vertically aligned, this one. And then we have done the sensing. We have started from the room temperature. We got very good response. This one you can see in the blue color. We got the very good response at room temperature. But in the room temperature, drawback is there. We cannot, this one, recovery is there. That one is not possible. That means we cannot use for the multiple times here. So what we have done, we have attached with the external heater, and then we have started giving the thermal activation energy here. So what is happening, NO2 is adsorbing on the MOS2, but this one is not desorbing this one, okay, making the stronger bond. To make this one here, to break this one, we have to give some energy in the form of the thermal. So we have increased temperature from room temperature to this one 100, this one 50 degree, 100, 150. And now at 100 degree, we got the complete recovery, this one. Here in this case you can see in the this one horizontally aligned, here is the vertically aligned, and if you see the sensing response, this one thing is that by the temperature basically this one we can get the complete recovery. Another this one here, if you see the 100 degree centigrade, this one here, this response is decreasing, because when we are giving the this one, when we are heating, our gas molecules also start the desorbing, and because of this desorption, what is happening, this one, our responsivity is there, sensing response is slow here as compared to the room temperature. But same time we have to compromise. We have two parameters. This one is recovery. If you want the recovery, then we have to compromise with the response here. Okay, so in this case, basically here we can reduce this one. Response is there. This one is reducing, but complete recovery we are getting. And now if you compare this one both in horizontally aligned and vertically aligned, here response is around 24. In this case, response is around 48% is there. So by growing just vertically aligned, we can improve the sensitivity almost double. This one we can do this one. That means if we play this one with growth, and if you can grind this one, grow the vertically aligned, our response is almost basically twice as compared to the horizontally aligned. Another parameter is there. That one is the basically how much this one selectivity is there, because that is very important. So we have used this one this NO2 is 5 ppm, other gases, basically we have used the high concentration, this one, and we found this one, this sensor is only sensing NO2, and when NS3 also small response, but if you see this one, change in the resistance is in opposite direction. So easily we can make out this one, our sensor is there. This one is basically our sensor is giving change in the resistance positive direction or negative direction. Easily we can identify. Again, we have taken the high concentration of this one. So if you see CH4, CO2, this one, almost this impact is almost negligible. Only we are getting from the NO2. When we are using higher concentration, small response from NS3, but this one is in opposite direction. So this sensor is giving very good response towards the NO2 gas. We have also proposed the mechanism why we got the higher sensing response in vertically aligned this MOS2 flex, because in horizontally aligned flex, what is happening, this one bottom layer is there, this one is with the substrate, so gas molecules cannot go and interact with these bottom surface. So here NO2 can only basically react with the top surface here. So ultimately this one horizontally aligned is getting only one surface where this NO2 molecules can interact. But in vertically aligned, because both sides here, these NO2 molecules, they can take the electron. And when this one, both side interaction is there, that means overall this one, our change in the charge transport will be higher. So because of this reason, these materials gain this response is higher than the horizontally aligned. Again, we have played with the growth kinetics. In this here, what we have done, we have created this one turbulent flow. So in this one bigger tube, we have used the smaller tube, and in this particular region, we have created this type of the this one turbulent flow region is there. And because of this region, what is happening, this one, our growth is there. This one is totally, basically you can say, is disturbed, this one. And because of this disturbance, what we are getting the nanowires. These are the same MO3 and sulfur we have used this one. And here you can see these this one is the nanowire network is there here. So this one is the higher magnification, here is the lower magnification. And we have confirmed this one, this material is MOS2 by using this one Raman spectroscopy and X-ray deflection here. So this both technique, they have this one, we can confirm this one is the MOS2 nanowires, and we have published this data in the applied physics later. Then same, we have made the gas sensors. So basically our group is the first one who has made this one MOS2 nanowires by using the chemical vapor deposition. In this case, again, we have made the same sensor, 100 micron distance. Here you can see these are the network. So we can take the contact, basically here 2 contacts, and all these nanowires, they are aligned, and we will get the basically current conduction through this one here. So in this case, what is happening basically here, at this one we have done at the room temperature. Room temperature response is very good here. You can see at 1 ppm, but here issue is that this is not complete recovery. So this resistance is not coming in the initial stage. So then we have started the heating. So at 60 degree centigrade, we got the complete recovery. But again, when we are going at higher temperature, 120, our response is also decreased from 7% to around, you can see at 1 ppm, this is the 2% is there, because at higher temperature, NO2, your gas molecule is not reaching near to this one surface, because again desorption will start. So here we can reduce the operating temperature. In the previous case was this one around 100 degree. Here nanowires, we can do this one around 60 degrees centigrade. And again, if you measure the response time is very good. In 16 seconds, we will get this one response as compared to the metal oxide gas sensor. This one is the very good. Recovery time is, we have to wait for the around 3 minutes time, we have to wait here. So in this case, basically here by using the nanowires here, this we can reduce the operating temperature. We have proposed the mechanism, this one here, what is happening, this one thing is that because these nanowires, they are connected. So one additional here, your junction potential is coming, and in the presence of the gas, this potential is also changing. Another thing is that at the room temperature, what is happening, this one, oxygen is absorbing on this one, and now at low temperature, basically this oxygen desorption will start, and now NO2 will get the more sites to react with this one here. So after NO2 here, because already some oxygen is there, so NO2 here change is there, that one is less here. This is the depletion region is there. So how much depletion region change is there? But in this case here, the change in the depletion range will be higher. So this one is the here depending by NO2 how much change is there. In this case only green region is there. In this region basically here because of the oxygen here is high, but at 60 degrees centigrade this oxygen is dissolved. So because of this one, NO2 change in the depletion region is high. But again, this maintaining 60 degree or 100 degree, that one is the challenge. And because growth is taking place at above this one at 150 degrees centigrade, so fabricating this micro heater is also challenge here. So we thought, can we use basically some this one photo activation method, because now this gallium nitride technology is mature and everywhere we are using this light emitting diode. So what we have done, we have used around 130 milliwatt LED, and that we have taken near to this one. This one is the 30 milliwatt LED, and then we have taken near to our gas sensor. So definitely, because this one is a UV LED, so MOS2 will absorb these photons and give change in the current here. But another here, what is happening, we can play with this one here. When we are increasing the intensity, basically our current will also increase. So one effect is coming because of the MOS2. Another one is coming because of the depletion. That means oxygen is absorbing on the surface, and when we are shining basically light, this oxygen is dissolved and we get only response from because of the MOS2. And another, this one, your photons will be absorbed and create the electron and hole. So our base current is there, that will increase in this case. So in this case, we have used the horizontally aligned this one. So you can see very nice this one, each flex triangle here you can see. And by the AFM, we have calculated how many number of monolayers are there. And we found this one, these are not single monolayers, around 4 monolayers are there. These are the bond, basically how this one is vibrating in this direction or this direction. Accordingly, we will get the A1, G1, E2, G peak is there. Here we have compared this one at room temperature. MOS2 is giving the good response, but here issue is the recovery. At 100 degrees centigrade, we got the good recovery, and at the UV, this one under the UV, your photo activation, we got the very good response and recovery here. We got very good this one response and recovery here. So particularly in this case here, if you compare this one at the UV, basically response is increased this one as compared to the room temperature here, and as compared to the photo activation, this response is the very high is there here. Okay, so we are getting basically, we are getting here, we are getting the very good response under the UV activation here. This one is the dynamic characteristic of sensor is there when we load the gas and when we remove the gas. Basically, again, this one is coming in the initial stage. This one, how much change is there? So we got basically very good response. This one in this case here. If we compare the response time here, generally because room temperature almost, this one is not the your complete recovery. Here recovery time is 71 seconds, and now in this case is the here 29 seconds is there. This one is the response time is there. So at room temperature, response is higher. In this case, 100 degrees lower, and 50% we can improve this one under the UV activation case here. So by using this one UV here 30 milliwatt LED, we can make the room temperature gas sensors. Here is the again response. This one is the absolute value is highly sensitive. This one NO2. This concentration also, if you see, we are taking the very high concentration, almost is negligible, and this resistance is in opposite direction. So easily we can identify. We have proposed the similarly mechanism. You can see in this paper ACS sensors here, because at room temperature, what is happening? This one oxygen is absorbing. With temperature, we are removing the oxygen. Under UV is also doing the same work here, is basically giving the energy in the form of the photons and removing this adsorbed oxygen. Now NO2 is here getting the sufficient site as compared to the temperature. Otherwise, we have to increase the high temperature. But same time, what will happen? NO2 desorption will also start. But in this case here, NO2 will absorb this one on the sides. So we will get the higher change as compared to the other room temperature or temperature. Another case is there. That one is this one defect engineered vertically aligned MOS2. Generally in the semiconductor devices, defects are not useful, but in this one gas sensors, defects are useful basically. So what we have done, we have created some intentionally vacancy by heating this MOS2. Sulfur is coming out here, and then we have also decorated with the RGO here. So we have made this one, we have converted basically this N-type MOS2 to P-type here by using this technique. How we have this one characterized, this one, how we have made, you can see this one in this one. So this one is our vertically aligned sample is there. We have uniformly this one distributed the RGO on this one. Next, these are the TM here. We have identified this one, where is the MOS2 and where is the RGO. Now you can see when we have created the vacancy, here we got the MOLI in the XPS, MOLI 6+. This one is the MOS2, here is the RGO decorated, and here is the first we have created the sulfur vacancy, and then we have decorated. And then we have compared this one, all three studies, this one. What is the impact of this one, RGO and sulfur vacancies? So what is happening this one here, this one is the basically RGO peaks, different binding energy peaks. So what is happening when directly when RGO we are decorating on the MOS2 here is making the weak van der Waals force is there. And when we are creating the vacancy and then when we are making this one is the strong covalent bond is there here. And because of this strong covalent bond, our semiconductor is there. This one is converted. This one is converted from N-type to P-types, this one. And that we have seen, observed in the sensing mechanism also. So you can see here the resistance in the previous case, resistance was in this one was positive change resistance. Here is in the negative direction. And this region is there. This one is the basically, this one is the particularly, this one is the because of here, because of this one change in the change in the type of the semiconductor. Type of the semiconductor. Why this one different type of the this one is there here. Just a minute. Okay, so because of this one change in this one, we are getting the change in the resistance in opposite direction. Also, we have done basically this one here, how this one is changing basically with the selectivity, and this one is highly selective towards the NO2 gas here. So what is happening here, you can see the mechanism, and now from MOS2 these electrons they are transferred in the towards the MgO type, and now this material when electrons are transferred, this one became basically P type from N type to P type here. And now you can see the holes, particularly this is the N type MOS2, and this one is the basically P type. So now the conduction is there. This one is the through holes here. And now in the holes, you know now the change basically from the holes, if you are taking the electron, their carrier concentration will increase. And when their carrier concentration will increase here, they will get the basically when carrier concentration will increase, their change will be in opposite direction. There, this one will be in opposite direction. So by using this one, we have created this one and from N-type to P-type semiconductor. Another one is this one. We have grown this one MO2 and MO3 hybrid structures. MO2 and MO3 structures. Okay, so in this case, what we have done, we have played with the growth mechanism. So we have grown this one. We have grown this nano flowers by using basically this one chemical vapor deposition. And here we have played with the growth kinetics, this one at different temperature. We have grown this one here. So we have played this one and then we have grown these nano flowers. So first thing is there here, where is the MO2 and where is the MO3 is there? How to identify this one? Yeah, just a minute, 1 minute.
Sir, can you hear me? Hi. Hello, sir. Can you hear me?
Yes.
Yes, sir, we can hear you.
Sir, I have one basic question related to the substrate. You are growing molybdenum disulfide over a silicon dioxide substrate. I have a basic question that the 2D material are very sensitive to strain.
I think
Sorry,
let the
can you hear me?
talk. Yeah.
Yes.
I think let the talk be over, then we'll have the discussion. Okay, Professor
Okay, sir.
Kumar can continue.
I'm sorry, actually. Yeah. So basically, then we have grown these nanowires, these nanoflowers by using this CVD. Yeah, so we have grown this one nanowires. We have grown these nanowires, and next we have characterized basically how these nanowires. So how this grown material is MO3 or MO2 is there. So basically what is happening, this one, we have done the XRD, and XRD we have this one, got the both materials here. We are getting this one, MO2 and MO3, both peaks we are getting. Same in the Raman spectroscopy, also we got the both peak here. So that means here, these nanoflowers are having the both MO2 as well as MO3, both they are having particularly. So now how to check basically where is the MO2 is there and where is the MO3 is there? We have done the cathodoluminescence mapping by using this one, and in the cathodoluminescence, what we have got this one, we got basically in the cathodoluminescence, basically we got here basically in the this one MO3, inside this one is the basically MO3 and outside is the basically MO2 is there. So we have done the mapping. So by using this one mapping, we have basically realized this one here. Inside the flakes basically is MO3 is there, here MO2 is there. So by using this one cathodoluminescence here, we can identify exactly where is the MO2 is there and where is the MO3 is there. Again, XPS is giving the both combined. We have made again the sensors and we have characterized this one, and we found particularly in this case basically here, what is happening, MOS2 and this one, as compared to MOS2, we got the higher response, this one, and at room temperature, we got the room temperature. Selectivity is also this one good as compared to the other materials. And then we have proposed the mechanism, and we are getting the response because of the barrier. When this barrier is modulating in the presence and in the absence of basically these gases in NO2 gas. So whenever this gas is coming, before gas basically this barrier is less, now barrier is increased. So because of this one, resistance is there, this one is increased in the presence of NO2 gas. We are also working on the other 2D materials. So we have done the DFT calculation. First, we have the collaboration with Professor Manikandan from IIT Jodhpur. He is doing the DFT calculation for us, this one. And he suggested this one. This is the another material is there. This one is giving the higher sensitivity as compared to this material here. And he suggested this one by the DFT calculation. This one is the highly selective towards the NO2 as compared to the other materials here. And then we have started growing this material by using the chemical vapor deposition. And we have done basically this one. So here again, we have grown the vertically aligned, because you know in the vertically aligned, the sensing response is higher as compared to the other structures here. So we have grown this type of the basically this flow. We have to play with the kinetics. This one, diffusion and adsorption stage is there, nucleation is there, and then finally growth is the vertically aligned. These are the this one different zone temperature is there. And you can see very nice flex. These are the vertically aligned. We have characterized by the Raman spectroscopy. And in the vertically aligned, we know basically this A1G peak is there. This one is more dominating as because we have more number of basically modes, these atoms as compared to this one. So we got the higher response. Again, we have made the this one sensors. I will not go in this one. I think I am approaching this one time here. So again, room temperature here is also the issue is with the recovery. In this case, response and recovery is very good. We have proposed the mechanism same here. Thermal activation energy is there. This one is converting, or you can say is removing this one adsorb oxygen, and because of this one here at temperature we get the higher response. This one is highly selective is having the very good dynamic response. And then again we are creating now this one some nitrogen doping, and we found by using this nitrogen doping again around 50% response we can improve just by doing the nitrogen doping here. We are planning, because these sensors, this one current is in microampere, so easily we can connect with our microcontroller, and we can use the Wi-Fi module, and then we can transmit this data. And heater, we can on these heaters we can integrate with this one, or we can use LEDs this one, and then we can make these sensors. So with this one, I would like to conclude my talk. We have grown the 2D materials. This one, different nanostructures. We have compared their sensing response of horizontally aligned and vertically aligned MOS2 flex. Also, we have made the room temperature NO2 sensors by using the photoactivation and by introducing the defects engineering and decorating with the RGU. Also here we have this one, I have shown some data on SNS2. This one recently this published in the Sensor and Actuators B, and we are improving the sensitivity by using the nitrogen doping. So mainly this MOS2 work was done by the Rahul, and Ashok now is working on the this one MOS2 and SNS2. Nilu MTech student C worked on this nitrogen doping, and funding we this one got from the CRB. With this, I would like to thank you everyone for listening me, and if you have any question, you can ask me.
Okay, thank you, Dr. Kumar.
Yes.
For the talk. I think I open the session for discussion now. So any questions, you can please raise your questions.
Yes, if anyone has Any question, please?
There was one, Dr. Altlaf Rahman, I think, where he is now. He's no more online. He had some questions. Dr. Rahman? Okay, it seems there is no question. Thank you, Dr. Kumar, for the talk.
May I interrupt, sir? Dr.
Yeah,
Altaf is online.
Okay.
Hello, sir. Hello, sir.
Yeah, please.
Thank you for your nice talk, sir. Really, I see it is very good work and good presentation. I have one basic question related to the 2D material growth on a substrate. 2D material. I see you grow 2D material on a silicon dioxide substrate, but we know the 2D material are very sensitive to strain. Can you just explain that? What are the effects due to the strain and the electronic properties of the molybdenum disulfide monolayer?
No, one thing is there, definitely temperature growth, temperature is there. That will create this one strain, different type of the strain. Okay, when we are growing at different temperature, these layers, strain will be different. Another thing is there, if you want to do the strain, basically, we can deposit another material on this one, or we can do the doping this one. By the doping also, that your crystal structure is there, that we can change.
But you presented the bench structure. I see that the bench structure is preserve their original property as the isolated monolayer.
Oh, that strain is not coming in that case. That one is the gas. Actually, electron transfer is taking place.
Okay.
Okay, charge transfer, when gas molecule is coming between molecule and this 2D material, charge transfer is taking place.
Okay, thank you, sir.
Okay, but if you want to do the intentionally, basically strain effect, this one, you can create the strain by different mechanisms, this one.
Okay.
Yes.
Okay, thank you, sir.
Yeah, thank you, Dr. Rahman.
Any questions? Anyone? Okay, thank you, Dr. Kumar, for your talk. I think you highlighted many points about the gas sensors and how they can be made for or used for the room temperatures also. So I hope your works will have better sensors in future with your works. So I thank you for your talk, and on the behalf of organizers, we thank you very much for your time. Thank you so much, sir.
Yeah, thank you very much. Thank you.
So with this, we come to the end of this session, and we'll have a break of around 10 minutes. And after that, we'll start with our session again at 12:10. So thank you, everybody, for patiently being with us, and we'll be happy to have you again after a break of 10 minutes. Thank you all. Yes.
Welcome back, everyone. So now we are into the invited talk session, the first technical session, invited talk session. Here in this technical session, we are going to have two invited speakers, Dr. Bahadur Singh from TIFR Mumbai and Professor Sunita Srivastava from Punjab University, Chandigarh. So in the previous session, we had a talk from Dr. Manish Kumar, keynote speech from Dr. Manish Kumar. There, I believe we all had a wonderful experience, and we all learned from him a very informative ideas about this gas sensing material that is designed using MOS2 and SNS2. So in this first technical session, the first speaker, Dr. Bahadur Singh, we will hear about Dirac, Weil, and higher fault fermions in topological quantum materials. So that will be the title of his talk. Dr. Bahadur Singh is currently serving as a reader in Tata Institute of Fundamental Research, Mumbai. And his research group have predicted for the first time several new Weil semi-metal candidates that are not limited to one material or a single family. And they also realize that various different types of emergent single Weil fermions, I breaking, T breaking, type 1 or type 2, double Weil, and higher fault fermions, also using novel force principles approach. Following their theoretical predictions, LAALGE has been confirmed experimentally as the first Weil semi-metal that holds Lorentz violating type 2 Weil fermions. Well, CO2 MnGa has also been confirmed as the first 3D topological magnet. His research group also proposed new concepts such as topological charge density wave insulator, saddle point, Van Hoff singularity surface states, Hoff and chain link topological states, Kramer's Weil fermions, among others, and predicted their robust materials candidates. Their works have opened new research avenues for theory and experiments for fundamental science and technological applications. And Dr. Bahadur Singh already has a Google Scholar citations of 1,735, H index of 16, and he is now currently working on topological quantum materials, low dimensional materials, and many body states in materials, theoretical design of quantum materials. Now, I will take this opportunity to invite Dr. Bahadur Singh to give his invited lecture in this first technical session.
Okay, okay. Thanks for this nice introduction. Let me share my screen. Okay. Whiteboard is there. What is happening? Is my screen visible and I'm audible, I hope?
Yes, sir. You are audible and visible.
Okay, because it somehow is showing my screen is paused. So I don't know if my screen is moving or not.
Sir, can you change to the next slide? We'll see
Yeah,
if
I'm
it moves or
already
not.
on the next slide, but somehow it's not look like to me.
No, it's not moving. Your screen is not moving.
Okay, so let me again share. Share. Okay, I hope now it's moving, right?
Yeah,
Okay.
we can see your cursor and it's working. Yeah.
Okay, thank you. Okay, thanks for the introduction, and let me start by thanking the organizer for putting this nice event together and having us here. Today I'm going to talk about Dirac-Weil and unconventional fermion with special context to topological quantum materials. Actually, recently what happened, the condensed matter physics system has recently becomes the fertile ground for realizing high energy phenomena, particle and phenomena in far more accessible condensed matter scale. This happens because in high energy physics, the particles are constrained by the symmetries of Poincare symmetries, that is symmetries of free space, whereas in low energy, they have to just follow a subset of Poincare symmetry, that is symmetry of 230 space rows. As a result, we can have a classification which can go beyond the particle that exists in high energy physics. So my group have been extensively involved in predicting these new phenomena as well as materials. And many of these are realized experimentally now. Of course, this work is not possible without the support of graduate students and postdocs, as well as my experimental collaborators around the world. So we can hear and more about our research work and group can be found at our website at TFR. Okay, with that small, let me give the outline of my talk. I will firstly talk about what is topological electronic structure, since it has been told like we have students as well. So just for sake of completeness and the introduction, I will start with what is topological electronic structure and how those electronic structure can allow us these exotic particle beyond Dirac and Weil fermions. And then I will briefly talk about our methods of choice. We combine first principle theories along with our various developments to predict the material platform for these exotic states. In second and third part of my talk, I basically focus on topological insulator, which has Dirac fermion state over the surface, and whereas in topological semimetals, we have these exotic states in the bulk of the valence zone. Okay. And then finally, I will summarize my talk. Okay, let's start with topology. Basically, it is a branch of mathematics that used to study the properties of objects that are invariant under smooth deformation. So here, smooth deformation is important because continues in parallel to the smooth deformation in condensed matter physics, we have adiabatic continuation, where we can see that if a smooth changing in Hamiltonian, it stays on the ground state of a new system. Okay. So in that sense, if we consider the objects which are invariant under smooth deformation, what that means is, suppose this is a sphere and it is equivalent to a wine glass. In this sense, one can transform from here to here without changing some property, and here that property is hole. And but this wine glass is not equivalent to donut now because it has one hole, but this donut is again equivalent to coffee mug. So this kind of characterization and the converting this geometrical objects or geometrical properties into a classification or global topology is provided by a famous theorem in mathematics that is known as Gauss-Bonnet theorem, that actually is the language of converting this local curvature into the invariants, where this G defines the genes or the number of holes in the object. In that sense, if we just look over these two objects, they have the same genes, 0, whereas this is not. Similarly, after the realization of integer quantum, after the realization of integer quantum Hall effects, we consider the similar analogies and find out we have a block states in a brilliant zone. And if we consider that total Wavy flux inside the brilliant zone for occupied state, that acquire a number, global number that is either 0 for normal insulator or non-zero for integer quantum Hall effect. So basically in condensed matter physics, these geometrical properties of wave functions are essential to describe the topology. Okay, too technical, so let's go how we have to understand it. Okay. So we know, let's go back to our condensed matter based on electronic states. Based on electronic conduction, we define states into insulator, semi-metals and metals. Let's focus just on an insulating state. There we have a well-defined energy gap separating the occupied states with the empty conduction bands. Just consider three different insulators. One is covalent insulator like silicon or gallium arsenide, where electrons are shared between them. And if we look for their band structure, we can see a gap between valence and conduction band. Similarly, in argon, the electrons are more localized over atomic side, and they also have a band gap roughly of 10 electron volt. And this is, one can consider this equivalent to vacuum with a band gap of 10⁶. So according to topological band theory, insulators are equivalent if one can interpolate continuously from one end to other without closing the band gap. Okay, so in that sense, one can see all the insulators are similar. Then what's new here? So then news are actually the topological states of matter. Let's see that with an example of well-known or the prototype example, bismuth selenide topological insulators. Okay. Now, if we consider just a simple ionic model, we can see bismuth has electronic configurations, outermost configuration 6s2, 6p3. And selenium is in P4 state. So in this sense, if we just try to make a simple ionic model, then selenium has strong tendency to take electron. As a result, okay, I know something happened. So this one, okay, yeah. So as a result, the selenium will take electron and stay in the valence band, whereas bismuth in the conduction band. So this is a normal insulating step. So if we start bringing both together to an atomic or to a material limit, so we can see they acquire a band structure. Again, valence is composed of selenium and bismuth, conduction with bismuth states. And what if we include spin orbit coupling, very strange thing happens in this sense. This bismuth state, which has strong tendency to give electron, basically start taking it because it's in valence band now. Similarly, selenium become unoccupied. So this is something which is not linked with the atomic insulator or not linked to the normal. So this state, and if we start plotting its wave function, just looking over here, the wave function will look something like this one, where we have the blue region outside and we have an empty region somewhere. So these two states are not topologically equivalent, and one can see they have described was based on some numbers, Z2 numbers. I'll explain in few slides. Okay. So basically in condensed matter, the band inversion dictates the change in topology, and this is one of the essential conditions for realizing a topological state. In rest of the talk, I will stay on this regime where inverted band side. Okay, now from here, let me tell you a few things why we require now first principle methodologies to study these materials. So although we know telltale signature for any non-trivial phase is band inversion, I just described by taking this selenide. So information of wave function structure in case space is very important. Now, if we go for low energy physics, one can deduce the change in topology using the low energy theory, various theories. However, one can exactly determine the state if we have the information of material electronic structures. And this is only enabled when we real model particular material structures. And that's why we look for these first principle approaches and then look for the their silent band structure characteristics. Okay, so now another important property of these topological states is, let's again with the help of this topological insulators, they realize a very fancy state over the edge over sample. Now this is called bulk edge correspondence, because as we discussed, this area is non-topological insulator with band inversion, whereas normal vacuum we already described is an normal state. So they have to go from topological to normal. So one must have some gapless state somewhere, and that exists at the this interface between the topological or normal insulator, or in other sense over surface of a system. Okay. And the low energy excitations around these states are described by Dirac equations. So these are basically mimic the Dirac fermion of high energy physics. Okay, So now how do we determine based on just electronic structure if system is a topological insulator or not, or system has a topological state or not? So we actually look for certain symmetries that can be spatial or non-spatial, and then try to deduce the information from the materials band structure and wave function. So here in left and right, I'm just showing the two cartoons of a normal insulator and topological insulator and their surface structures. If we say in normal insulator, they also have a state, surface state, but one can remove these states by just changing this Fermi level up and down. With you can use this by doping or by just removing some dangling bonds states. So these are not robust. Whereas in case of topological insulators, these are basically a Kramer partners. So one cannot, and they exchange the Kramer partner as these trim points, and one cannot remove these states just by changing the Fermi level. You can do, you can shift this Fermi level, but you always have this crossing in it. So these are protected, but this is always not easy to calculate the surface electronic structure. So what we can do is we have a certain symmetry in the bulk and then calculate these numbers or topological invariance from bulk states. Here is an example of simple inversion symmetry. Based on that one, we can easily calculate the invariant with simple formulas. Here, this is nothing but just a parity eigenvalue of a state at a trim point gamma I. So in the 2D Brillouin zone, we have 4 trim points, gamma 1, gamma 2, gamma 3, 4. And then M goes from 1 to N, that is occupied states. And just by simply counting the occupied, counting the states with positive and negative parity in a system, we can determine the Z2 number. Similarly, in 3 dimension, we have various another topological invariants. So overall is just looking over the symmetry properties of the bulk, and then with the information of our wave function, we can determine all these invariants or the topological states. Okay. Okay, so while looking over this structure, by now we have various kind of materials, topological materials in insulators as well as in metals. We have Weil semi-metal. These are not merely now a prediction or the theory, but they are well realized in experiments. We have Weil semi-metals such as tantalum arsenide, lanthanum aluminum, germanium, or many others. We can have triple point semi-metals where you can see the doubly degenerate band crossed with singly degenerate, or Dirac semi-metal nodal fermions, and similarly various classification of insulators, crystalline insulator, higher order insulator, or axion insulator. So basically now we have topological material ranging from insulator to metal, semi-metal, and semiconductor, and then the new field is coming as the topological magnets. And since these properties, these states or their properties are protected by bulk states, so properties are protected by the bulk state, so they can allow us very fast and low power electronic and spintronic devices, and moreover they can be used for the disorder free quantum information science and technologies. Okay, so far so good. So let's do how we employ and what is our theoretical roadmap. So basically, generally in an electronic structure person, people only focus on first principle calculation and try to compare with experiments. However, we find like although this method is little accurate, but it is computationally expensive because for extended modeling various experimental properties, for example, RPS or transport experiments, it's very difficult to employ that in direct first principle code. So what we did is we tried to employ these first principle theories and generate the material specific tight binding and K dot P models, such as linear functions, and now we can develop this side, we can calculate various properties depending on, we can add interaction, we can add all kind of effects into. So this route employ the user development with the manageable computational cost. And I will show in the next few slides how this route is so successful in predicting the various topological materials. Okay. So we are extensively applying this route instead of directly going from first principle to experimental comparison. Okay, with that, let me talk about our first prediction. Earlier we did this work. I started very long before when I was a graduate student at IIT Kanpur. So we looked for, at that time, we were just looking for what are the new topological materials. And And I always talk about this system because I'll show it has a very fancy property which one can show how robust data topological state is. Okay. So if we look over the periodic table on this side, because this is a heavy atomic number regime, and so they may have automatically have inbuilt large spin orbit or relativistic effects. And if we consider the crystal structure, they have a layered crystal structure, but without any weakly coupled pair, as in case of bismuth selenide. And moreover, they have both normal and topological insulators. As a result, they can allow various phases. We can have a topological phase transition. We can have a wild semimetal like eye breaking, or can have a Dirac semimetal has a critical point, or just by looking, changing the thickness of the slabs, we can also realize the quantum spin Hall insulator in the systems. Okay. So if we look over its bulk bands, here, this is important because one has to determine the symmetry properties of the states. And symmetry properties we can determine just by looking for the crystal wave function by exploring in terms of the atomic wave function and determine their symmetry properties. So here I'm just writing the atomic wave functions and the associated symmetry properties, which are given by the reducible representation. So if we just look over without spin orbit coupling, this is zoom in around along this point. So we have a small band gap. As we include spin orbit coupling, then this blue region, which are basically coming from antimony piezo, that comes to valence band and the other goes to conduction. So there is a band inversion in this system. And if we calculate the invariants, if we calculate the topological invariance based on the method I discussed earlier, like symmetric arity, we get that Z2 is equal to 1, 0, 0. Okay. So if we look over its surface, now there is something funny here, because due to inversion symmetry, and also it has a layered crystal structure. So, and moreover, if we just looks of the interlayer distance, the distance between thallium and selenium layer is large. This is 3.30. So it's natural for crystal to flee between them. However, if we go with the T1 termination, we end up with terminating the surface layer with selenium atoms. And in another layer, if we terminate along this particular point, and then we actually terminate it at the thallium layer, or it can also have the possibilities which can end up with terminating 50-50. So we can have this kind of rough surface. Okay. The point why I highlight is these two terminations gives us a polar surface in this sense, because we are breaking a strong bond, so they must have a independent electron over them, which are unpaired. Whereas in this case, due to this 50-50, okay, one can realize actually a non-polar surface, and we will see what their effect is. So if we go for this T1 termination, we can see first of all this due to bulk topology, it has a Dirac cone surface state, but additionally it has these states where this red color I'm showing the surface state wave localized over the surface layer. So basically this has only localized on the surface layer, so one can identify them as the dangling quantine states. If we go with T2, the Dirac cone state still stays there, but we have additional states. So situation is complicated, although bulk topology is there. So it's one. If we go for this 50-50 termination, we very strangely we find like we get a clear linear dispersion over surface. And this is well compared with the experiments, and so an experiment also find like this particular systems as this kind of rough surface. So we can see like in a rough surface, the carriers are more easy to move. So in that sense, they acquire a Dirac dispersion over a rough surface. So that shows and this is dictated by bulk topological structure. So these state the topological states are more robust. They can exist on this kind of complicated surface morphologies. Okay. Now, in parallel to this, if we look for, so another point is, so far we just looked for these states which have a Dirac dispersion or near the Fermi level. Now one can start asking another question: can semimetals or metal can be topological? What that means is, can they have gapless but topological states, as we just described in case of topological insulator? Then the answer is of course yes, and then that is a critical point. And what happens to this critical point? If we combine this critical point with various crystal symmetries, then this critical point is actually stable over a substantial region of parameter space, and then we can have a topological semimetals. And based on the crystal symmetries, we can have Dirac semimetals. That is what, if a system has inversion symmetry, time reversal, or some additional crystalline symmetry. And moreover, these points actually exist either on high symmetry K points or rotation axis. Now, if a system has planar symmetries, planar means like a mirror plane or PT kind of symmetries, then we can, this Dirac cone can extend cross over remain connected through a forming a loop in K space, then we can have nodal line semimetal. Now, if we break either time reversal or inversion in these semimetals, we can have Weil semimetals where low energy excitations basically are Weil fermions. So this is in a chiral basis, one can separate this Dirac 2 into 2 Weils by just breaking the time reversal symmetry. Okay, so then let's see, let's focus on the Weil semimetal. But what are those actually? They provide the realization of Weil fermions. So we have the solid state quasi particles. And if we start looking for a massless Dirac equation, we start solving the massless Dirac equation in high energy physics and separate based on the chiral basis, we actually end up having Weil equations, which is the two copies of Weil fermions are separated in K space. So these, so here what I'm showing is a cartoon picture which shows the two Weil nodes. So their characteristics is they over the surface, they should have a Fermi arc states. Okay. And if we look over their Hamiltonian, this first term is energy lowering, energy rising, or maybe kinetic energy term we can consider. And the second term, which include the all three Pauli matrices. Okay, so if there is a local perturbation and we add that perturbation, that cannot remove these gapless points. In other sense, they just change the dispersion. So these states are more robust as long as the bulk translation symmetry is intact, or we cannot combine these two Weil fermions. Okay. And moreover, depending on this kinetic energy term dominance in the system, we can have two type of semimetals. One is type 1 or type 2. Type 1 has actually Lorentz invariance. Strictly, they still follow the Lorentz invariance. What that, whereas in type 2, that is broken. That means electron and holes have a same carrier velocity along subtend direction. So they have the directional dependence transport in experiments. Okay. So we discovered various families of this type 1, type 2, or of the Weil semimetal. And in this talk, I will be focusing on just one material candidate. That was the first type 2, is lanthanum, aluminum, germanium. Okay, looking over its crystal structure, it has a tetragonal unit cell. If you see, this is its tetragonal crystal structure without actually inversion symmetry. Okay. If we consider just look over any atoms, you will just doing a simple R minus R translation. We cannot end up at the same point. So that means it's broken. Moreover, it has a screw C4 screw rotation symmetry. So if we start from one atom, we end up with second, third, and fourth. Okay. So these are just shown with this one. This is the associated crystal structure. Although system does not have inversion, but it has various mirror plane symmetries. So that means like the various bands can remain crossed along these mirror planes. So this is the bands without spin orbit coupling. We can see various crossing along high symmetry direction. If we explore in the full brilliant zone, these crossed along the mirror planes. So here is showing this is a highlighted region is basically mirror plane, whereas this crossing is nodal lines. Along with that, we have the gapless Weil nodes. Okay, since system don't have inversion symmetry, they can allow it. If we include spin orbit coupling, these crossing at certain point is gapped. If we look for the full brilliant zone exploration, we can get there. We can find like these gapped into a nodal, the Weil nodal points, and these are actually distributed across the mirror planes. So we can have a 40 Weil nodes, and depending on their energy dispersion, we can classify them based on W2, which are having type 2 energy dispersion but lying away. We have W1 Weil node, which have linear dispersion but actually away from the Fermi level, or the W3, which is also quite away, far away from the Fermi level. So then the experiments are performed on the system by Professor Jaidasan's group at Princeton. And if we see in the first map, we are showing actually KX KZ plot at Ky is equal to 0 plane. And if these are our simulated energy dispersion or the simulated Fermi surface, and they have a quite substantial matching. And at certain point, the KZ of W2 mirror planes, which is accessed by some polarized the energy of 542 electron volt. And if we start zooming in here at one point, and we can say this can be a touching point between electron and hole pockets, and that can only be verified if by changing the Fermi level, the size is changes. So if we see, if we change the Fermi level to 25, this particular size start increasing, whereas other decreases. So this is a whole electron pocket and the other is hole pocket. Okay, so we have actually find a touching point, these wild nodes as a touching point between electron and hole pocket. If we go further and start mapping its EK dispersion, we can see along Y direction, there is a tilting or type 2 dispersion, which matches quite well with the calculated dispersions. Similarly, along X direction remains linear, whereas similarly along Z direction. So it's linear. So this is actually after tantalum arsenide, which is determined with the type 1 fermions. This is the type 2 wild fermion semi-metal. Okay, with this, so let's go to okay. So similarly, more recently now we are started looking over their magnetic counterparts and see how magnetic symmetries shape these wild fermions. We recently find the cerium aluminum silicon. It shows a totally new kind of non-collinear ferromagnetism as well as having wild semi-metal. So this is the first non-collinear ferromagnetic wild fermion semi-metal. So what actually ferromagnetism does here is it tune the location of these wild nodes. Although wild nodes are created already by inversion breaking, but this it tunes the wild node locations in the system, and this has a very pronounced effect over the transport. So we actually determine the first new kind of Hall effect, that is loop Hall effect in these systems. Okay. Now, if we go for a full family picture, one can change this lanthanum with cerium, praseodymium, or all rare earth, and then we can have a very rich kind of topological structures. We can have all varieties of wild fermions, which are actually excellent platform to explore the correlated phenomena in this topological material family. Okay, now let's, so I hope I have some time. Okay. So let's go for this one quickly over topological nodal line semi-metals. So these semi-metals are basically, if in a system we have additional mirror planes or the planar symmetries, then what happens if two bands with opposite mirror eigenvalue connect, then they remains connected over a mirror planes. As a result, they form a nodal line. And this nodal line from here, there is no energy high, there is no high energy analog. And we can have a topological invariant kind of winding number gives similar to this very phase. So they can have a filled surface state which form the take a form of the drum head. So they can actually term as the drum head surface states. Okay. So depending on what's this number is, these drum head states either lies inside or they can lie outside of the nodal dispersion. And what we try to do is we actually looked over material system and tried to design the new topological semi-metal while playing with the mirror symmetries in a system, because we know there are many mirror symmetry already existed. So we find like if we have a conventional ring kind structure, if we combine these two rings, they can cross each other and forming a half link, or one can have outer chain or inner chain. And they have their own characteristic properties. And in this sense, we just look for this cobalt manganese gallium, which is the well-known Fullier-Slush system, having very large Curie temperature of 690 Kelvin. And in this one, if we look over the spin down state, this has a whole pocket at gamma point, whereas on spin up state, there is a crossing along gamma to K. And if we chase this crossing in full brilliance zone, it form a very rich nodal structure. We can have a half link, we can have outer chain or inner chain structures. Okay, based on this design principle, this was basically highlighted at editor suggestion earlier. Then again, Professor Hassan's group at Preston, they looked into the spectroscopies of this system, and they find clearly a nodal ring structure in the system. And if this is actually RPS map, and this highlighter or the these are the overlay from the first principle results, and we can see they are quite substantial matching with this one. And so, and moreover, they also have the extensive surface state which can exist in this Hopf length. So this is basically determined, or this is basically verified as the first ferromagnet in systems. Okay. Similarly, while playing with these various mirror plane, we can have a different kind of rich nodal structure. For example, here we can have this fancy star fruit like nodal structure, where this crosses along one mirror plane at one side of the brilliant zone and crosses on the other side, just below the KZ is equal to mirror plane. And this is all, so we can also have crossover from this topological or the nodal line semi-metal to insulators. Okay. Now let's go beyond that. So far, what I tried to say, and I hope okay. So we have a threefold. We can also have a threefold fermions. So basically, in condensed matter physics, system has to follow a subset of Poincare symmetries. So the underlying concept is we have to determine the higher fold irreducible representation at certain points and lines, and which allow actually the fermiology of this higher fold system. So we can have wild fermions where we can have crossing between singly fold bands. So at crossing point, it's a two-fold degenerate. In Dirac semi-metal, this is two-fold degenerate point. So the crossing point is four-fold degenerate. And additionally, if we have a system without inversion symmetry, but having a mirror plane and a rotation symmetry combined, or a non-symmetric symmetries, we can also have a crossing point between 1 plus 2 or 2 plus 1. So this kind of system is basically a threefold fermion systems. And we design methods to how to predict. So far, basically, there were various systems predicted, but they are not that clean. So we just let's look for ideal Dirac semi-metals with C6B symmetry, and then start breaking this symmetry. So what we did is, with those spin-off, this is just a cartoon showing a singly degenerate band and doubly degenerate. If we start bringing them together, they cross at certain points. So this is without spin orbit case. And if we include spin orbit, they again become two-fold degenerate, and due to this C6 symmetry or C3, they cross here. So these are a stable Dirac point. Now, if we break the inversion symmetry, this one state separates and then realize the triple fermions. And this has been actually proposed in a new material of VAAZES that clearly shows triple points without spin orbit coupling. This point is basically triple point. And if we include spin orbit, that transitions to a Dirac semi-metal, but it can bring back to triple point just by breaking the inversion symmetry. Okay. And so why now, just while looking for the various irreducible representation and symmetry properties, we can have all kind of exotic two-fold fermions. We can have three-fold or four-fold as well as six-fold fermion, and their corresponding topological characterization is there. And moreover, there is a rich exotic state called chiral crystals, which we have predicted. They can realize basically all these fermion states, and these are actually experimentally determined, experimentally verified by now. Okay, so with that, let me see. So what next? So far, we are looking for these exotic states in the condensed matter system. So where the field is going. Basically, now it's a full-fledged field that combines theoretical physics, material science, as well as their device properties. So I put it as a quantum information, since they can have a protected phenomena. And if one couples various degree of freedom under the umbrella of quantum materials, like how various degree of freedom couples with topology and gives a new responses, we have a whole new field of topological condensed matter physics and material science, which can also have inbuilt correlation. So basically what I'm proposing is awakening two different kind of quantum interaction in the materials. Okay. With that, I actually summarize my talk. So this is take home summary is basically all the exotic Dirac wild and unconventional fermion can exist as low energy excitation in materials. So one can realize their associated non-trivial physics in just tabletop experiments. And based on our first principle theories, as well as combined with our own approaches, we determined various families of topological materials. Today, I talked basically on thallium bismuth class of topological insulators and lanthanum aluminium germanium class of wild fermions, as well as the nodal lines and triple point fermions in VAZ. Thank you. And I will be happy to take any questions.
So the speakers has talked on direct, while and higher fault fermions in topological quantum materials. If there is any questions or any comments from any participants, now it is open for discussion. Anyone from the participants? So I believe there's no question or no comments from the participants. Even though the concept is a little bit new to me, because even also working on this material science, but I have not read into this particular issue. So it was really very informative and really very interesting to hear from our resource person who is from TIFR Mumbai. Our institute, even though it's a very small institution in the northeastern corner of India, this is the second speaker we have from Tata Institute of Fundamental Research, Mumbai. So Dr. R. Vijaya Raghavan, I think our speaker know him very well. He also visited our institution in August 2019. That time we organized one workshop on quantum information science, and Dr. R. Vijaya Raghavan agreed to travel all the way to our institutes, and he delivered a very interesting and a very informative lecture on quantum computing and simulations and all. So our institution, even though it's a very small institution, we have a kind of long association already with TIFR Mumbai. We thank you, sir, for taking our time and sharing with us your recent works and this very informative new ideas about this topological quantum materials. Yeah, thank you so much, sir.
Thank you.
Now we have come to the second part of our invited talk. So before I invite our next speaker, I would like to announce here again that our program is being live streamed in our institution YouTube channel, and all the lectures, all the videos will be available even after the conference is over. So if any participants or anyone is interested to go to those lecture videos again, you can visit to our institute, Pachu University College official YouTube channel. So this, I believe we can make use of this channel, and we can revisit the lecture and come up with like new knowledge. So our next speaker is Professor Sunita Srivastava. She is a professor in the Department of Physics, Punjab University, Chandigarh, and her research interest is on 2D materials, DFT calculations, nano-confinement, nano-heterostructures. She has worked as a teacher for more than 30 years now, and she has published over 60 research articles in reputed journals. We are glad to have you here with us, Madam. So I shall now invite Professor Sunita Srivastava to give her invited talk. So, Madam, I will just make you as a co-host so that you can share your screen. Just 1 minute. I actually forgot to. Yeah. So let us now invite Professor Sunita Sravastava to give her invited talk.
Thank you very much. I'm very glad to be part of this conference. And I must admit that, we have had Dr. D.P. Rai was once with us as NASI fellow. And he worked with me for around 2 months. And I was, very much impressed by his hard work and the dedication to the subject. And it was a wonderful overlap. And I'm happy that he is part of the organizer of this international conference. And it is a great pleasure for me also to deliver a lecture here. So let me just share my screen here. So I hope, is it visible?
It's visible, Madam.
You
Yes.
could confirm. Yeah. So presently I am in Central University of Haryana on deputation basis. It is, 2D materials are really wonderful to work with because, every day you have new physics coming out of it. And it has, I have spent, I think, around more than 15 years now on these type of areas. So today I'll be discussing on topological semi-metals using first principles. And coming to the background, I think Dr. Bahadur from TIFR, he has made my things very, very simple. And by explaining what is Weyl and Dirac and metal and so on and so forth. So it was nice to hear his lecture also. So that made a basic sound background for the participants, and so I can easily miss out those fine details. Okay, let me make this full screen. So I believe this is fine. Okay. So I'll be talking on topological semi-metals using first principles. So my talk would be, organized in this fashion. That first of all, I'll be talking about the thermoelectric materials. What are those and why we need them? And then we go to introduction to topological materials. And coming to my work, how the rare earth monopnictides have important role to play these days, and why is it in research, and why we have started with lanthanum bismuth. And I'll then let you know, I'll discuss and I'll share with you how the first principle calculations have been performed on this system, and what are the list of software codes which I have employed. And then, of course, coming to the properties, in addition to structural and electronic properties, I'll be talking about mechanical and thermodynamic properties as well. And then the thermoelectric properties, and then I'll conclude my lecture. Of course, there is energy crisis, and we are all looking for alternate energy resources, and thermoelectric materials have come to our rescue. So thermoelectric materials, they find significant applications, as you know, in various energy saving methods and even the power generation in refrigeration. Of course, two parameters which characterize these thermoelectric materials are figure of merit and power factor. So you can see, that in the figure of merit, you can see on the numerator, you have sigma ST. So here, the electrical conductivity, the Seebeck effect, the temperature, and the KL and KE. So electronic contribution in the lattice contribution to the thermal conductivity and so on. So we have to play around with these parameters and increase the efficiency of both through dimensionless figure of merit ZT, and we want to have large power factor. But then as you can see in the figure of merit, K must be a small. So it is a challenging task because it is a combination of conflicting physical quantities which are coupled with each other. So examples of these materials are schutterides, clathrates, transition metal chalcogenides, Heusler alloys, and topological insulators. So because they have large thermoelectric efficiencies, so topological insulators, they form excellent thermoelectric materials. And these materials, they are characterized by narrow band gap, which is associated with the band inversion. So of course, in the previous lecture, you must have seen that how the band inversion means, what it means. And of course, it is consisting of heavy atoms, which helps us to maintain the low K value. And the charge transport in these materials is dissipationless. This is very important. That means, there is suppression of backscattering, and, that leads to a good thermoelectric performance of these materials. So we have the research, and myself too, and my group, we have concentrated on topological semi-metals. So what are these topological semi-metals? Because they are different from topological insulators. So here, topological semi-metals, here the surface state possesses high carrier mobilities. So, and large value of magnetoresistance. So here, it is classified into 3 types, about which you have just heard now in the previous lecture: Weil, Dirac, and nodal line semi-metals. So the transformation of topological semi-metals from one form into the another by breaking one or more sets of symmetries make their study more important. So whenever we try to break the symmetries, the transformation takes place, and that is the crux of the matter. So here, a similar type of explanation here we can see in the diagram. You can see, there is a spin orbit coupling and the band inversion. So this spin orbit coupling, it opens a full band gap, a full gap after the band inversion in a thermoelectric insulator. And therefore it gives rise to surfaces which are, surface states which are metallic in nature on the surface. And whenever we talk about Weil semi-metals, semi-metal or Dirac semi-metal, the bulk bands, they are gapped by spin orbit coupling in the 3D momentum space. So you can see that this topological insulator, you have a gap, but here, there is a contact point. There is a isolated linearly crossing points, and these are known as Weil points or Dirac points. So this becomes a 3-dimensional analog of graphene. So here the topological surface states appear on the surface, and they form exotic Fermi arcs, as you can see here on the surface. And if you talk about this Dirac semi-metals, they have, they doubly degenerate. Like in Weil semi-metals, the degeneracy is lifted due to breaking of the inversion symmetry. So ये type 1, type 2 Weil semi-metals के, you can see the picture where, you can easily see that in type 1 Weil semi-metal, this Fermi surface, it has shrunk to a 0 at the Weil point. This is known as Weil point. And here the Fermi energy is sufficiently close to the Weil point. And in type 2, there is a tilting of the Weyl cone, and therefore there is a touching point between electron and hole pockets on the Fermi surface. So with this, I move on to explaining that of topological insulators. What are they? So you can see here, if you try to see uh, this diagram, you can see that this is a conduction band, this is a valence band, and this thick line represents the Fermi energy level, which is present in the middle of the band gap. And you have, this particular line. So this is a Fermi level, and this line is basically first Bragg's plane, which can diffract the two energy states and open the band gap here. So so what happens is that the particle energy, it increases till it reaches the wave vector pi by a, and once it reaches here it because it encounters the first Bragg's plane, therefore there is a diffraction, and it gets strongly diffracted, and this is how a band gap, there will be an opening there will be a band gap. Okay, so the particle, this is follow this energy path. You can see this black arrows representing that. And what are these gammas and pi by a? As you all know, these are high symmetric points in the first billion zone. And this V, which we have here, they represent the diffraction potential. And it is, you can see, symmetrical about the Fermi energy. So you have, band gap equal to 2V. And then we come to topological indices. Of course, it relies on symmetries of the system rather than the Hamiltonian. And there is in the Weyl semimetals, they exhibit genuine quantum phase transitions between gapless states, and you can easily tune the chemical potential to a nodal Weyl point. So here there is a mirror symmetry, and Hall conductance, which we talk about, there is a discontinuous quantized jump there. So these transitions, they are not only limited to the gap states of matter, they can persist in a true metallic state also, where you have an extended Fermi surface and a finite density of delocalized states at the chemical potential. So there is a sharp quantum phase transition between the topologically distinct metallic phases and the topological metals. Okay. So you have all these things, and because it can be this very definition of topological states, it can be extended into a gapless metallic phase. So this is the whole property which we are looking after. And there is always an unbroken symmetry which is required to enforce the identity of such a topological metal states. So why we are interested in rare earth monopnictides? Of course, you know what are monopnictides. Nictogen, these are chemical elements in group 15 of periodic table. And they are also known as nitrogen family, and they consist of nitrogen, phosphorus, arsenic, antimony, bismuth, and there is another one. That was, I think, Moscovius or something. So these materials, they have 5 electrons in the outermost shell, out of which 2 are in the S shell and the 3 are in the P shell, which are unpaired. So, these are 3 electron short. So this was the definition of monopnictides, just to share with you. And this family of rare earth monopnictides with lanthanum in the material. So, for example, LAX. So X can be anything, phosphorus, arsenic, antimony, bismuth. So because they have large magnetoresistance and there are possible topological states which can be associated with these materials, and that is why they are very popular these days. And there are a number of attempts, both experimental and theoretical, where, lanthanum bismuth, it's found to exhibit large magnetoresistance and high carrier mobility. In addition to that, you have huge bulk conductivity. So because of their high melting points, extreme hardness and mechanical strength, they can be used for hard coatings and magnetic storage devices. And the RP's investigation, which you can see in the diagram, it shows, here you can see in the figure. So here, the existence of surface states that is confirmed because of these 3 Dirac cones which are seen in the RP's investigation. One appears at the brilliant zone and the 2 at the corners. So there is a band inversion along the X direction, and there is a presence of one massless and one gapped Dirac-like surface state. An odd number of Dirac cones were there, and this suggests that there is a non-trivial band topology of lanthanum bismuth. So first principle calculations have been done, and node line-like surface states have been observed, which is plays a significant role in their large magnetoresistance behavior. Okay. So there have been many theoretical attempts to investigate these type of materials to calculate Z2 invariant from bulk and surface band structure and so on and so forth. Of course, here, because I have used Z2 invariant, so I must tell you what it is. So it is a topological invariant, which is not an integer, but rather a churn parity. So it can be either odd or even, and it is called Z2 invariant. And जब भी time reversal invariant is taken of these electron system, so here all energies eigenstates they come in degenerate pairs. So here only electric field is allowed and so on and so forth. So if you are interested, you can go into the details. And there are other theoretical attempts where you can see that it has been proved that it acts as Z2 topological semi-metal and so on and so forth. So we have a number of theoretical attempts. So coming straight to our present work. So here, these semi-metals, thermoelectric semi-metals, topological semi-metals, they enhance the efficiency of thermoelectric devices because of their large electrical conductivities and low lattice thermal conductivities. So we have performed first principle calculation to calculate their properties, and we justify, their candidature for futuristic thermoelectric devices. So अभी हम detailed investigation में जाएंगे, and we see that we have, I have listed here various computational details which have been used. So here VN2K code has been used to calculate the structural, electronic and thermoelectric properties by using full potential linearized augmented plane wave method. Okay. And then, coming to exchange correlation potential. So all those who are well versed with DFT calculations, they must be aware that we talk about the exchange correlation potential there, and the local density approximation, the modified Beckey-Johnson potential. We have carried out with these exchange correlation potentials with and without spin orbit coupling. So all those who do not do DFT calculations, for them also the results would be very interesting. And this is just for those people who are into it and who want to do this DFT calculations. So the cutoff energy was taken to be -6 Rydberg, and value of RMT into K max. These are just the settings of that. So in addition to the VN2K method, we have used Bootstrap code and Gibbs code and Phonopi software. So Phonopi software, this is used to find out, the phonon dispersion spectra. And this Phonopi software, of course, I'll tell you in our subsequent slides that it is based on density functional perturbation theory. So when you come to VN2K code, so just to have an introduction to this, so we see that in the DFT calculations, the VN2 program is based on the augmented plane wave plus local orbital method to solve the Cohen-Sham equations of density functional theory. So we represent this solid by a unit cell, which is repeated in all the three directions corresponding to periodic boundary conditions. So here we, of course, assume that solid is a perfect solid, ordered and infinite. So we do not have any boundary conditions with that. Okay. And in this method, in this particular method, we consider all electrons, core as well as valence electrons, and self-consistently, we use it in a full potential treatment. So here the unit cell gets decomposed into spheres centered at the nuclear sites and an interstitial region. So these atomic spheres with radii RMT can be set automatically in an optimal way using the set-termed utility in VN2K code. And the Cohen-Sham approach we follow, it needs an exchange correlation functional. So, because we do not know the exact functional and approximations are needed, therefore we go to local density approximation and the generalized gradient approximation, meta GGA or hybrid functions, depending upon what type of system we have and what results we are looking for. So you have a GUI interface, and that is a very easy to work with, and it can be accessed by any web browser. So various steps which are involved is first you generate the structure, and then the input generation, and then the self-consistent field cycle is used. You can calculate all these things: energy bands, density of states, electron densities. You can also go for photoelectron spectroscopy, which includes both valence band and core level photoelectron spectroscopy. The optical module here, you have you can calculate the direct transition between occupied and unoccupied states. For both states, Cohen-Sham eigenvalues are used. So magnetism also, hyperfine fields and electric field gradients. Then this is a bootstrap program about which it has been written down. So you have all these points, and let me not go into the detail. The transport theory has been used here. So this gives a method to calculate the thermoelectric transport coefficient, and it also describes the evolution of a distribution function under the effect of external electric field and the temperature gradient. So this distribution function, it provides the probability of finding an electron in band with wave vector k. So, the distribution function can be obtained by solving the Boltzmann transport equation, which is, you can easily see here, which consists of all the three contributions: field, scattering, and diffusion, and so on and so forth. So you have to use relaxation time approximation, and which represents the time taken for an electron distribution to relax to the equilibrium Fermi distribution from a non-equilibrium state. Then there is a Phonopi software, and you prepare a unit cell, you relax the structure, build set of supercells with displacements, you calculate forces on atoms of the set of supercells, collect set of forces and phonon frequencies. So this is an open source package, and it it is used for calculations at both harmonic and quasi-harmonic levels. And then you have Gibbs software. It uses quasi-harmonic Debye model, and you can find out Helmholtz free energy as a function of temperature. So Gibbs function की बात करते हैं हम इसमें. We talk about Gibbs function, and then we find out the other macroscopic properties and so on and so forth. So the running time is less than 1 second for 25 EV pairs, 10 pressure and 10 temperature values. So it is very easy to use. Now coming to my system of LABI, I talk about this. So this you can see. So this after the software section is over, we can talk about various the system and its properties. So this is the system which we have, lanthanum bismuth. This you can easily see it crystallizes into FCC structure, and it has space group symmetry FM3M, and this is the positioning of lanthanum and bismuth atoms. So if you use all these three things, so we have this energy to volume curve from LDA calculations. So you have a minima here. So you can see LDA and GGA both have been used in this work initially. So you have 6.49 lattice constant and 6.65 here, and experimental value is 6.58. So, so both are in good agreement with the experimental values, and you can see the bulk modulus also. So LDA is a better option. Okay. So but then we have used all these things. We have investigated the electronic properties by local density approximation. Then we have added spin orbit coupling, and this is MBJ modified Becker-Johnson potential with the spin orbit coupling. So you can see here, that at high symmetry point X, there is no band inversion. So both conduction band and the valence band, they merge with each other near the high symmetric point X. Whereas when you have spin orbit coupling, so they give rise to band inversion between this two symmetry points, gamma and X. And this orbital character of band changes near the X point. This confirms the topological character of lanthanum bismuth. So you can see that this is lanthanum 5d orbitals with even parity, and this is bismuth 6p orbitals, which has odd parity. And these two orbitals, they have contributed to the band inversion. So this energy gap is found to be 21 millielectron volts, which agrees with the 19 value. Okay. So the two match well. And the third case, with this third case, we can see that the conduction band minima near the X point, it has shifted upwards, and the valence band maxima at the gamma point is pushed downwards. So there is a band inversion is still there, but it is consolidated by increasing the band overlap. So this band gap is 17 MeV. So this band inversion gap is, you can see this is, clearly visible in the inset here in the diagram. Okay. So let us talk about the other property, total density of states. So you can see here, so it is mainly contribution from lanthanum d orbitals and the bismuth p states. So here, as you include the SOC effect, you can see that the total density of states, it has increased from here to this value in the conduction band region, which is beneficial, for enhancing the figure of merit of the system. So these are the different definitions or arithmetical formulas, and this is the stability criteria which you must be aware of. So all these have been used in this study. So these are the values which has been calculated. So you have the parameter Y, the Young's modulus, which is 60.04, and you have the Poisson's ratio, which is 0.33. So they show stiffness and the nature of interatomic forces of this compound. Okay, and you have these constants, you have shear, elastic, anisotropy, okay, and you have bulk modulus and shear modulus. They tell you about the anisotropic nature and the strength of the resulting material. And we have also Puck's ratio, which is a ratio of B and G, the bulk modulus and the Young's modulus. This is found to be 2.59, which is greater than 1.75. So iska matlab, this shows that it is ductile in nature. Then we also talk about G by B ratio, which is Frantzevich ratio, which comes out to be 0.38, which is of course less than the criteria 1.06 that shows less resistance against shear deformation. So this is how we calculate the mechanical and thermodynamic properties. This is the phonon dispersion spectra and the DOS curve which we have. So these are the various things, 64 atoms in 2 by 2 by 2 supercell, and Phonopi code has been used. The phonon frequency is increased from 0 to 4 terahertz. So, there is no negative frequency, which shows the thermodynamic stability of the material. And whatever there is a mass difference between lanthanum and bismuth atom, this is, manifested into the shape of the phonon dispersion curve. And this is the partial DOS, which tells you about that the lanthanum and bismuth, they contribute almost equally for generation of phonon frequencies. So you can see their contribution. These are acoustic. The lower frequencies, they correspond to acoustic phonons. And, so the contribution here is more from the bismuth part. It dominates slightly over the lanthanum, whereas when you talk about the optical frequency mode, so here the contribution from lanthanum dominates. So, this is the phonon dispersion curve. Then we talk about the thermoelectric properties, the chemical potential dependence of transport coefficients. So, the plot has been from minus 1.5 to 1.5. Okay. So the positive part. So you can see that the negative trends of the curves from minus 1.5 to 0. Okay. So you can see as with the temperature increasing. So you can see the effect, and in the range 0 to 1.5 electron volt, it depicts N type of carrier, and here it depicts P type of carrier. So you have both all the things, Seebeck coefficient, you have electrical conductivity, the electronic part of thermal conductivity, and the power factor. So they have their maximas. So यहाँ पे minus 62.43 units. Here you can see there is a 4.51 into 10 power 22. So you can see here the value, and here you can see the maximum value which is obtained is 0.9 into 10 power 16. So these values, they lie in the range, all these values lie in the range 0 to 1.5. So basically that shows that it has N type of behavior. So which is consistent with the other studies. And with the doping level, so you can see this is N type of doping and this is a P type of doping. So, basically you shift the Fermi level to the two bands and try to, analyze the properties when the doping is different. So this doping level is there, and these parameters which has maximum, these have maximum value in the negative range. So you can see this has maximum value in the negative range of the doping level, which again confirms the N type of behavior. So, so you can see all the 4 graphs here. And then coming to the thermoelectric properties, the Slack equation has been used. Here M is the average atomic weight, delta is the average volume of mass, delta cube of mass equivalent to 1 atom in the primitive unit. Theta D is the Debye temperature, T is the absolute temperature. N जो है number of atoms per unit cell, and gamma is the Bunsen parameter, which has been you have these Poisson's ratio and all that defined here, the coefficient A, and so on and so forth. So these are the thermoelectric properties. You can see the Seebeck effect, Seebeck coefficient. Basically, it increases with the temperature. So this is negative here values, you can see. So though the trend, the curve decreases down, the value of Seebeck coefficient, it is increasing, the mod. So it is because of the lifting of band degeneracy by the induction of spin orbit coupling effect. So you can see the difference also. There is a SOC curve is slightly higher than the curve without SOC, spin orbit coupling. Similarly, that of the electrical conductivity, it all increases linearly with T because there will be large number of thermally excited charge carriers present at high temperatures. And then you have the power factor. This is found at room temperature. It is found to be around 0.46 value, okay, around 0.46 value at 300 Kelvin. And it further increases to 1.34, you can see, at 1000 Kelvin, which is very large compared to Weyl semi-metals and topological insulators. And also heat conduction, if you talk about, it also increases with increase in temperature. And this is KL, the lattice thermal conductivity. You can see this decreases. This is what was required. This decreases as the temperature increases. So because of the lattice vibrations and so on, increase in the frequency of lattice vibrations and large phonon scattering. So this is a characteristic of efficient thermoelectric material. And then we talk about the total thermal conductivity also. There is a decrease with T because electronic thermal conductivity, it dominates over the lattice thermal conductivity. So it is same case as that of Dirac semi-metal. So figure of merit is shown here. So here also you can see the spin orbit coupling plays a very important role. So there is an increase in the value of ZT, and it is due to two factors, that because there is an increase in the power factor with increase in temperature, and also there is a decrease in value of the lattice thermal conductivity with increase in the temperature. And iska matlab, so you can see here that ZT value can be increased at higher temperature. So that means that this particular material, it can be a very promising material if we have for a application which is a high temperature application. So we conclude the lecture today. We see what all we have seen. The structural, electronic, mechanical, and thermoelectric properties have been studied using first principle calculation, which has been combined with Boltzmann transport theory. The lattice parameters are in agreement. The lattice thermal conductivity is 15.91, which decreases with increase in temperature and reaches a minimum value at 1000 Kelvin. So this is a beautiful result which we have got. And even the power factor, it is found to increase with temperature with maximum value of 1.34 into 10 power 13 at T is equal to 1000 Kelvin. So it is an efficient thermoelectric material, as I've told you before, because of the large PF and low KL. And figure of merit also increases with temperature and attains a maximum value of 0.42 as temperature is raised from 200 to 1000 K. So these findings, they suggest that it can have a beautiful high temperature applications. So these are the collaborators with whom we have worked out this particular study, and this appeared in Physics Letter A journal in 2020 in December, and we were very happy with it. And let me thank you all for patiently hearing me, and let me see if I can. if I have some questions, I can answer. Any question from the audience?
Yeah, thank you, madam. So now I invite the audiences, the participants, to comment on the talk or raise any queries.
Can I ask question?
Yes.
Yes. Dear Madam, at the beginning of your presentation, you mentioned that the semi-metals have no backscattering of electrons, as I see. And what is the reason of the absence of the backscattering?
See, I showed you one diagram, if you remember. I showed you this diagram. Okay.
Madam, can you share the diagram once again?
This is the diagram. Can you see?
Not yet, madam.
No,
Please
I
share the screen.
Okay,
share the screen, madam.
Okay. Let me share the screen. Okay. You're right. Yes, let me share the screen. Oh, yeah. Right?
Oh, yes.
So here I did explain about the topological insulator. So what you are asking is, you can correlate with this. So what I have shown here is that here, once the particle energy is increasing, okay, and when it reaches pi by a value, the particle, it encounters the single Bragg plane diffraction, okay, and this diffracts the particle. So this is the reason for opening the band gap. So if there is no band gap, so this kind of diffraction is not there. It is not encountering that brilliant zone. So it's not encountering this single Bragg plane. Okay?
Any other question from any audience? If there are no other questions, I think I should now invite Dr. Divya Prakash Rai, if he has any comments.
Hello.
Hello, Divya. How are you?
Good afternoon, ma'am.
Nice to see you here. Oh, yeah. After a long time.
Nice to see you too, ma'am. I'm fine. And
nice.
And thank you for a very informative talk. And I am very closely connected to Professor Sunita and her group. And I have already worked under her, under Icmsap fellowship. And from her only, I learned about 2D systems. Actually, I was working only on the bulk materials. But after joining her group, I came to learn about these 2D materials, and she helped me in understanding this, the 2D properties of graphene-like materials. And she also helped me in, like some computational techniques and computational code, Siesta. I learned from her, and that helped me a lot. And working in Siesta, I have published at least 5 papers. So thank you very much, ma'am. And another good thing is that, like, through ma'am, I'm able to link with Professor Tankeshwar Kumar also, who is a very renowned physicist of our country. And I'm not personally connected to her, but every time when I try to, mail him or message him, I just go through ma'am only. So ma'am is the medium through which I'm linked with Professor Kumar. And one more thing is, like, from Professor Sunita's group, we have 3 speakers, ma'am herself, one more speaker delivering her invited talk tomorrow, Dr. Kulvinder Kar, and one more professor from her group, Manish Kashyap, who is the professor in JNU, will be delivering his talk on the final day. So, so we could, I mean, it's a big contribution from our group that we are getting 3 best speakers. So thank you very much, ma'am, and for all your help.
Thank you. It is always pleasure. It is always pleasure whenever I hear from you.
And because of you, ma'am, like we could install a siesta code in our lab also. Now, some of our students are working there in siesta code. Thank you, ma'am.
Wonderful. It is nice to hear that. Thank you.
So I think we shall now thank our speaker, Professor Sunita Srivastava, for her wonderful talk in this session. We shall now have a few minutes break. Our session 2 will begin at 2 p.m. today. There we will hear from Professor R.J. Musembi from Kenya and Professor L.A. Fomin from Russia. And Dr. Divya Prakash Rai, the convener of this conference, will chair the session. So I thank all the participants. I think we can now have a short minutes break. We can join this meeting, this conference, once again at 2 p.m. To attend the day 1 session 2 invited lectures. Thank you all. Hello, friends. We are about to start our session 2 today. Dr. Divya Prakash Rai will chair the session. Before we begin session 2, I request everyone to kindly mute their Zoom. Kindly mute your Zoom before we start the session.
Welcome to activity mic. Activity.
Welcome back, everyone. So my name is Dr. Alfred Zola. I'm one of the convener of this conference, and Dr. Divya Prakash Rai will be joining us in few minutes. So in the meantime, I think we should go as per our schedule. So today in session 2 of this day 1 of this conference, we are going to hear from Professor Robinson Musembi, who is a professor of condensed matter physics at the Department of Physics, University of Nairobi. We welcome you, sir, in this conference. His research interest is in thin films and thin film devices like solar cells, solar thermal observers, gas sensors, optical thin film applications, and he also works on computational method, and he's proficient in programming techniques using C++, Python, Microsoft VBA. Professor Musembi graduated with a PhD at the University of Nairobi in 2009. He has been a postdoc at Armstrong Laboratory, Sweden, and Indian Institute of Technology, Roorkee, India. He has published several articles in both refereed journals and conference proceedings. He has also been to many scientific meetings where he has presented his work as well as participated in organizing scientific events. He has also contributed as a reviewer for several scientific journals. Professor Musembi is a member of several professional associations, which includes Kenya Physical Society, SSS, EESA, European Physical Society, ANSOL, Kenya, National Young Academy of Science, AMRS, Kenya. Today, he will talk on advances in solar cells, successes, and way forward. So we shall now invite Professor Musembi to give his talk. And to remind everyone, this invited talk is 30 minutes duration and 5 minutes discussion. Professor Musembi, I think you can proceed.
Thank you. Thank you for that kind introduction. My talk will be on experimental work, mainly, which we did in our lab some time ago, together with some other work. I hope my screen is visible to you. The title of my
yes,
talk,
sir, it's visible. Please go ahead.
Yeah, advances in ITER solar cells, successes and way forward. I'm based at the University of Nairobi, as you have been told. Let me start my talk. Okay, mainly, when we talk about solar cells, mainly we talk about the absorber material more than any other layer of the solar cell, because solar cell consists of very many layers, but the naming nomenclature, which is normally used, is the absorber material. For example, we have the silicon, monocrystalline, polycrystalline, the amorphous silicon. We have those ones which are based on chalcogenite materials, the dye-sensitized material, where the main material is the dye. We have the organic solar cells, and then we have the ITER solar cell, which is our talk about today. The ITER stands for extremely thin absorber. Then we have other solar cells like kesterite, and then the newer material, which is called the perovskite. ITER solar cell was derived from the ideas which had been obtained from the dye-sensitized solar cell. And if we can compare with the conventional solar cell, the PN junction type of solar cell, that is the silicon type, mainly silicon solar cell, the transport of the carriers is mainly the minority carrier type. And for you to fabricate a silicon solar cell, you require clean rooms, which means the material has to be pure, and superior technologies are required. And the principle of how it operates, it's on the light absorption, charge separation, carrier transport, or in one material. Now, when you compare that one to the dye-sensitized solar cell, the dye-sensitized solar cell is a bit different from from the conventional silicon solar cell, where we have the dye material, then we have the p-type material, then it requires an electrolyte, which will be replenishing this dye material with electrons, and then we have the counter electrode. The principle, mainly majority carrier type of solar cell, where the charge carriers are majority type. Purity, high purity is not required, which means you can actually use a very simple technology to fabricate the solar cell. The principle of the solar cell is a dye absorber. Dye absorb the light, then the charge separation, then the carrier transport, or which are separated in the whole material. Then from the dye solar cell, a new type of solar cell was derived there, which is called the ether solar cell. This type of solar cell, the absorber, the idea was to have an absorber material which is in the nanoscale, probably around 10 nanometers to less than 50 there, 50 nanometers. And that material, the idea was to sandwich the material between N-type and a P-type material. And then you can put the usual layers of the solar cell. This is solar cell. The way the work started was a few institutions. They came together and they obtained a grant with this kind of proposal of this kind of a solar cell, because many people thought that this type of solar cell will work very well because the absorber is very thin and the charge transport, it will be easily harvested. So one of the founder members of this project was the ECM in the Netherlands. Then we had Hermos Center, Berlin, which has actually initially it was called Hahn-Meitner Institute, because you can see the earlier logo, but that one has changed long time. Then we had the Tallinn Technical University. Then there was Uppsala University, then the TU Delft, Weizmann Institute in Israel, then University of Ghent in Belgium. Those are the initial universities which began this kind of work. For us to fabricate a solar cell, there are a number of things we need to consider. We need to consider the way the sun radiates the light, and it's governed by this Planck's equation. Normally, when we want to choose a material for solar cell, we need to confine ourselves between this region, in the visible region, between around 300 nanometers to 700 nanometers. If you confine your band gap within that region, then you are assured that your solar cell will be optimum. If we can just look at briefly the theory which governs the solar cell, well, normally the way we look at it, we look at it as if it has a diode which is in series and another resistor which is parallel to the diode itself, so that we can just, if we need to do simulation, that is the way we can follow. And if you just apply the normal Kirchhoff rule, then you come up with those equation 1 and 2, which can be derived further, and you include the series resistant, shunt resistant, and this one will be the light photon, the current, and whereby after dividing with the area of the solar cell you are fabricating, then you can get your current density. If you are interested in analyzing it further, something like a transport mechanism, then you can always manipulate your equation and get up to number 3, where you can get your VOC. using that equation. And then you can include the saturation current, the short circuit current together, and then you do your calculation very easily. These are just the theoretical predictions of how you can interpret the material if you are doing research on transport mechanism. Most of the materials which have been used so far in the ITER solar cell, they include the titanium dioxide, zinc oxide, niobium pentoxide, tin oxide. Those are mainly the P-type. During the research, mainly of the ITER solar cell, it was actually discovered that it was not easy for this solar cell just to work with the P-type and the N-type material alone. It required a buffer layer material, which had to be put between the N-type and the absorber material. And these are the main materials which were investigated. These are the absorber, mainly. Then the whole conductor, mainly captocyanide, copper iodide, the polymer material like a PDOR PSS, and the spirometal. The materials which I've marked in red, those are the material which I try to work on to see what kind of a solar cell I can produce. You can see the layout is very simple. You can have the spray pyrolysis, which you can assemble very easily using some beakers. And if you just have a compressor pump, then you are good to go. Other deposition methods are like the chemical bath deposition, where you don't need to substrate the material, just a beaker, a tripod stand, and the hot plate heater with a star. And then you can do your deposition. Then there's a technique called the successive ion layer absorption and reaction, whereby you simply dip in a precursor material, then you rinse, then you dip your material again, your substrate in the next material, then you rinse, and you repeat the cycle. So it is actually very easy, straightforward, without complicated materials. When it comes to analysis, I resorted to two kind of scanning electron microscope equipment, the one from Hitachi and the other one from Carl Zeiss. Although they just do the same work, it's only that whichever is available, you just use it. This is how your material look like, because we needed a material which has a very large surface. You can see it is highly porous. This is the P-type material when you look at it using the scanning electron microscope. Okay, and that is what is described there is the procedure which was used there in from the deposition up to annealing, so that you can get a crystalline material. Because if you just use it as deposited, it's actually amorphous and it's not even crystalline. So you have to anneal it at around 450 degrees Celsius, and then you can get your crystalline N-type material. There are several ways of getting the titanium dioxide layer. Like this one is deposited using the salt gel technique. This one is actually another very good idea if you need a solar cell with a very good blocking layer. You can use what is called a compact layer. These are other images showing the N-type material with the buffer layer. And you can see when you look at it, they are actually, this is a very high magnification, because it's like a magnification of times 1 million. So The pictures are very clear when you look at the thin film material. But when you look at it with your naked eye, it looks very smooth. You can't even imagine that this is how it looks like when you look at it using the microscope. There's still the same buffer layer. This is our absorbed material, and we managed to get an absorbed material in the range of almost 10 nanometers, which we could determine using by flipping the thin film on the SEM so that we can get the cross section. Now, for us to determine the band gap of the materials we were using experimentally, we used an equipment called the surface photovoltaic, whereby this is the setup where you put your sample there, and then you put a mica material. That mica material, it forms something more like a capacitor, and then you are able to measure your photovoltaic. And now, these are the results which are from the photovoltaic machine. And if you draw a tangent, you see you can easily get your band gap, and you can see from the TiO2, it's almost the same theoretical calculated band gap of 3.2, and mainly experimentally, which is available. This is indium hydrosulfide for the buffer layer. As prepared the material, we could get around 2 electron volts, but this one, after annealing, the band gap becomes a bit smaller. So for lead sulfide, although on the further analysis, we actually found this is not a pure lead sulfide. I think we will see that one a bit later, but the band gap was actually determined to be around 0.85 electron volts. On the further analysis of the materials which is deposited using the X-ray photoelectron spectroscopy, these are the results which we obtained. When you look at the indium hydrosulfide, we could find there was indium, there's also indium there in a 3D shell. There's also another indium. I think this carbon is like from, I don't know, whether it is dirt which was on during preparation, because none of our materials contain carbon, but you could see sulfur 2p, 2s, and the indium 84D. So for lead sulfide, we found that it is actually a mixed phase because on this shell, we found there is actually an oxygen there. Then the sulfur, the lead, and the lead. X-ray photoelectron spectroscopy can actually give you a lot of details on the material which you have deposited. The source for the gun of the electron, it was using the magnesium K alpha. This is the further analysis on the results, whereby you can see when you do the fitting, you end up with two types of lead. There's a lead oxide and there is a lead sulfide. But from the references, actually we could attribute some of the energies to the experimentally to lead sulfide at 137.3 electron volts. That one is also concurs with some work in the literature. And there is also at 138.3, there is also a lead oxide. So we concluded that this type of material was actually giving us a mixed phase type of lead absorber material. In our work, we also decided to try something like a polymer material as our hall conductor. And this one, we chose the PDOT PSS. And that is the structure which is given for PDOT. It's not a bad material. It has a good conductivity. The problem is the usual problem with the polymer materials. When they are exposed to the air, after some time, that material can actually degrade a lot. For us to put a back conduct, then this one was done using the vacuum techniques. And this is the kind of mask which we used. So our solar cells, they were very small, not so big. And this is the lab scale. Normally, when you are making solar cells in the lab, you try with a very small one, and when they become successful, then you can scale them up to the type we see in the market. This is the cross-section of our full solar cell, showing the different layers, and actually they could be identified, although it is not easy to identify the one for TiO2 with indium hydroxide and the lead. Then the P dot layer is clearly visible, and the gold back conduct. But for us to make sure that we are actually seeing properly, you can perform what is called the EDX mapping, which can actually give you an idea of which layer is lying where, and it can give it to you using a color code, and so that you can actually differentiate the layers from the cross-section, because initially when you look at it from scanning electron microscope, it's just a black and white layer, but you can, using EDX mapping, you can actually get the layers in color. Apart from the normal current voltage characterization, for us to get more idea on series resistant, shunt resistant, then we had to perform more experiment. This is the initial beginning of the work, whereby it shows the N-type material with the back conduct. It's like forming a shock diode, and you can see the way it is resistive, the way it is forming a very nice curve. And these are layers which are in that configuration, whereby you just have the fluorine doped tin oxide, then the N-type layer, and then the back conduct. Then you add more layers. You add the absorber material, the N-type absorber, P-type, and then the back conduct in this configuration of the layers. And you can see the performance of the kind of configuration is very poor, with the conversion efficiency of 0.01%, and not so good fill factor. The VOC also being not so nice, and the short circuit current density in microamperes. So that's the reason, and that was the everything which was affecting the ITER solar cells. None of them could perform with just the absorber and the N-type, P-type layers. So on inserting the buffer layer, you can see like there's some improvement but further tweaking and then also improving the deposition, the best we could get was actually less than 1%. Most of those ITER solar cells, they were not very good solar cells, but very good. Actually, if you are teaching somebody like the postgraduate student on how to fabricate the solar cells, they are very nice type of kind of a solar cell because they are very simple. The material, the equipment are very simple, and you can do the work very easily. We also would like to know how was the solar cell performed, because apart from when you are illuminating a solar cell and measuring the IV characteristic, you might not understand what is happening. So you measure what is called the external quantum efficiency, so that you can understand when you illuminate with the light, the incident photons, how many are being converted to electrons. You know, it is from photons to electrons. And this is the performance of the external quantum efficiency. And we could see that the percentage was not very good, because if you are to look at materials like silicon, you might find them with the external quantum efficiency of almost 90%. But the best we could get here, it showed that this kind of a solar cell had a lot of losses, because the incident photons, they are not even being converted to the highest of 16%. And we could say maybe that is what was affecting the solar cell to have that kind of very poor performance. So this is a part of the analysis to compare the results, the open circuit voltage, the fill factor, and the eta represent the conversion efficiency. The reason why I'm using U is because it's commonly used anyway. It's because the units for the voltage is also V. So instead of using VV, just use the U, which is also commonly used. This is the performance of the solar cell when you are trying a different kind of layers, and you can see there is one layer which was performing so well at 0.94, and then we could also determine the shunt resistance. And by the way, the shunt resistance, when it is very high, it means that your solar cell will also be performing very well, because most of the current which is being generated, it is not finding another route to escape to the other resistor in the series. This is the we tried also to measure the solar cell when you leave it in the solar simulator for some time. And this is the duration in minutes. From 0 minutes, you just measure, and then you leave it there. You see what happens. And you can see when you leave it, this one was left on the solar simulator for 180 minutes. And after few short duration, you go and measure and measure and measure. And you can see as you soak the solar cell, it improves in performance in terms of the conversion efficiency. So we wanted to understand what is happening by looking at different layers, and we could see some kind of a trend. And when you also do the same for the external quantum efficiency, you can see also the quantum efficiency, it's actually improving, because as prepared solar cell, this is where it is. And after 3 hours, after 24 hours, after 96 hours, this is directly without removing the solar cell from the simulator. You just leave it there for almost 3 days. and measuring after every duration of soaking. You just run the measurement and see what is happening. Further analysis, this is the analysis for the current voltage, and now by changing the temperature. This solar cell, we also performed some measurement by placing this solar cell at a very low temperature in a cryostat, which had a liquid nitrogen, and then the outer layer, it has the liquid helium, such that we could get a very low temperatures like 200 Kelvin in steps of 10 up to 320 Kelvin. And for each time, this is an automated system, which means it could perform the measurements from lower temperature, increase the temperature a bit, and do another measurement, and still measure that solar cell at a different intensity. The system is equipped with different shades, which are simply rotated by a motor, so that you can get a different intensity. Here, where you have 100% of the light intensity, it means that there is no shading for preventing the intensity, to reduce it, I mean. So these are the results when you are measuring at a different current, voltage, and at a different temperature. And you can see from 200 Kelvin as you go to 320, you can see the results the way they are. These are now the specific results, the open circuit voltage versus the intensity, then fill factor versus the intensity. Then we have the conversion efficiency versus the intensity, and you can see at a lower temperature we were having a higher conversion efficiency, meaning that temperature also it produces the phonons, and then resistant within the solar cell. So that's explain why we were getting a higher conversion efficiency when you are measuring at a lower temperature. Now, it comes to the fitting and trying to do some calculations so that we can get some information we need. This is the VOC versus the temperature, and then fitting so that we can calculate the activation energy. And this is the value we got of 0.79 electron volts. Then this one is the conversion efficiency versus the temperature at a different light intensity. We also from 0.05 milliwatts per centimeter square up to 100 milliwatts per centimeter square, going up like that. And you can see the conversion efficiency was improving as you increase the efficiency and also vary the temperature. Now, what do these results of ours tell us? The diode ideality factor. Remember that when you look at the equation of the diode equation, the non-ideal case, there is always the ideality factor. And this activation energy, there is a way you can relate it to the diode ideality factor, and then you get some information. So it means in the dark, the charge carriers undergo what is called the tunneling enhanced recombination, while under illumination, the recombination is thermally activated and occur through the exponential distributed recombination energy levels. Because when you look at our ideality factor, it was almost like approximately to 1. And why were these fluctuations being observed? This one is ascribed to the charge-discharge effect in the buffer layer. Now, when you look at the inverse temperature versus the reverse saturation current, we can still get some more information. There is a lot of theoretical work which has been done on how you can analyze the transport mechanism of the solar cells. In the dark, part 1 and part 2 are temperature independent, confirming a tunneling assisted mechanism, because you can see that the two are not related, and they are confirming that the recombination is a tunneling type, and under illumination, the recombination of the electrons, which are generated, is thermally activated. This one, it's when you plot the reverse saturation current, and then you get the activation current or activation energy of around 0.92 electron volts. And by the way, the activation energy we are talking about here is a bit different from the one which the people in a chemist, the one they talk about. So when we look at our two activation energy values, the one for 0.79 and the one for 0.92, you can see they are almost as if they are within the range of our the band gap of our absorber material. So what can we deduce from this? It means that the recombination process is taking place in the back of our absorber material. From the literature, because this work was not done by theory, it was by experiment, and it's not easy to get the valence band and the conduction band of every material. But from the literature, such information is available. And when you try to plot against the Fermi energy and plot the valence band and the conduction band level for each material, this is the kind of band diagram you can predict for this kind of a solar cell. And then now, can you remember the poor performance of this solar cell? You can see where we have the absorber material, the lead sulfide, and where you have the buffer layer, you can see there is a blocking layer. It means that the conduction band of the buffer layer and the conduction band of our absorber layer. Our absorber layer is like it was lower than that one of the buffer layer, meaning that the excited charges which are produced, in most cases, they are not flowing normally, but they are more like trying to tunnel to the N type because of this kind of configuration, which we can see from here. And normally, when we are fabricating a solar cell, we always want like the absorber layer, the conduction band, to be a bit higher, unless you want to produce those kind of solar cells which are called the quantum well. But for us, for this kind of a solar cell to perform very well, then we wanted it to be to have maybe the conduction band energy to be much higher than that one of the buffer layer, because you can see for the N-type material, when it's compared to the absorber, that one is okay. This one is higher than this other one. But the problem was the buffer layer, and this is the only type of buffer layer which could work well with this material. So explaining why we have so many losses, because the charges are simply trying to do the tunneling. When the series resistant is extracted and plotted on its own, that's how it looks like at different temperature. And you can see the series resistant was very high at a very low temperature, and very low at a higher temperature. Now, our conclusion, the TIL2 actually was found to be good, and it can be used, has been used widely as the window layer, the buffer layer. It added the suitable interface for the lead sulfide. It could be good for that kind of a solar cell. What we can say about the PDOT polymer material, it was more like a protective layer, because also even the lead sulfide could still, even if it is a mixed phase, it could still oxidize and form the lead oxide, and then the efficiency after some days, it could degrade a lot. Now, the transport mechanism materials, whereby we include the temperature in the current voltage characterization, we learned a lot, especially the recombination process, and where it is taking place. We could also predict the body diagram of the solar cell. And now, as a way forward, because these type of solar cells, they have been investigated a lot, and they are very good for fundamental research, meaning that if you want to train somebody experimentally how to make solar cells, the ITER type of solar cell, it's a very good candidate. But for you to understand further why it performs so poorly, perhaps the first principle method, like the DFTs, can be employed to try to figure out why does this solar cell perform so badly. Then perhaps, because we have seen even like the type of solar cell producing almost a transparent solar cell, meaning that a very thin solar cell still works. So it's actually methods with the better control for chemical reaction, which are required for us to do this work. And I would like to thank the audience and the organizers of this conference for giving me a chance to make my presentation. Thank you, and I welcome questions.
Thank you, Professor Musembi. It was a very informative speech. Any comments from the audience? Even though we have exceeded our 30 minutes allotment, if any comments is there?
Can I?
Yes, please go ahead, Professor Rajkumar.
Okay. That exhaustive study and the presentation. My name is Dr. N.S. Singh. So, Professor, I'm interested to know what is the optimum thickness of these ETA solar cells, and how we can obtain this optimum thickness of the deposited layers.
The optimum thickness in most cases is affected by the N-type layer, because whenever you look at the TiO2 material, in most cases, the one which works very well will always be around 1 micron and above. But the absorbable material, that one could retain at 10 micron. But the N-type material, your solar cell is not it won't work easily with a very thin layer, because we also tried the compact layer, which we could deposit even 50 nanometer thickness, but that kind of solar cell, the conversion efficiency is very poor. Only the thicker N-type material produces better solar cell.
Okay, thank you.
Anyone else from the audience? Yeah, before we thank the speaker, I just want to have one quick question. So in your presentation, Professor Musembi, we have seen that with the introduction of that buffer layer, there was a drastic increase in fill factor and also efficiency of that solar cell. So what exactly was the optimum thickness for? Did you optimize the buffer layer thickness, and did you try out different buffer layers to improve the fill factor and efficiency of your solar cell?
Yes, we tried different types of buffer layers for the indium sulfide, indium hydroxide, and this material called cadmium sulfide. But the problem with the cadmium sulfide, you cannot get cadmium sulfide with a thinner layer. So only indium sulfide and the indium hydroxide they could give you a thickness of 50 nanometers, and which is forming a nice layer, continuous, and it can work well for solar cell. I think the improvement with the efficiency when you introduce the buffer layer, I think it was improving the interface between the absorber and the N-type material, because without it, it's like there was a lot of recombination, and all the electrons you collect, they just get lost in between the interface.
Okay. Now, thank you so much, Professor Musembi, for your delightful speech. Now, I shall pass on the chair to Dr. Divya Prakash Rai. So let me now invite Dr. Divya Prakash Rai to chair this session.
Thank you, Dr. Shiata. Now, for the second talk of the second session, I will invite Professor Leib Formin, who is the head of the laboratory of Institute of Microelectronics Technology and High Purity Materials, Russian Academy of Sciences, Moscow, Russia. Professor Formin has experience of 23 years in research, and mostly his research interest lies in magnetic force microscopy, micromagnetic calculations, epitaxial nanostructures, ferromagnetics, antiferromagnetics, and spintronics. And today he will be delivering his invited talk on epitaxial films and low-dimensional structures made of ferromagnetic metals and half-metallic ferromagnets for spintronics and terahertz photonics. So over to you, Professor Formin.
Do you hear me? Oh.
Yeah.
And do you see my presentation? Oh. Oh. Do you see my presentation? I don't hear you.
Can you make your presentation full screen?
Is it not in full screen? Oh. No. No. Is it in full screen or not?
It seems, but it's small. Can you make a little bit bigger?
It is small? Oh.
Yes.
Now it is small or not? Why?
Sir, can you press F5 key to make it full screen? Your presentation.
Is it clear or not? I'm pressed F5 key and it is in the full screen now, but what?
Sir, at your menu bar on the left side at the bottom, there is like a button for your slide presentation. So please select slide presentation there. Move your cursor to the bottom on the left side. Yeah, left.
The presentation?
Yeah, no, below. Go down, your cursor go down. Move to the left.
Yeah.
It should be in slide presentation. If it is there in slide presentation, it should be fine, I think.
No. What can I do? Maybe it is in Zoom or not?
No, sir, it's not in full screen, but I think it's visible. It's really
it is visible now.
It is visible.
Yeah, you can go ahead.
It is visible. Maybe I will present in such a regime if it is visible.
Yes, please go ahead.
Okay. First of all, I would like to thank the organizers of the conference for the opportunity to speak, and I will present an overview report on the topic of our laboratory's work, namely of epitaxial films and nanostructures that we manufacture from them. Spintronics is a new and rapidly developing area of electronics. This area includes the development of spin logic and magnetic memory and other devices, in particular generators of terahertz radiation. We use the epitaxial ferromagnetic structures in spintronics because it is promising, firstly, and because they have regular magnetic structures, and secondly, giant effects can be observed in them. For example, the giant magnetic tunneling effect, which arises due to coherent electron tunneling in epitaxial ferromagnet dielectric ferromagnet heterostructures. Another example is the ballistic transfer of electrons in ferromagnetic epitaxial nanostructures at low temperatures. Micro and nanostructure ferromagnetic elements are used in spectronic devices as components of spin valves, spin injectors, and detectors. The size of micro and nanostructural elements used in spintronics are usually 0.1 to 10 micrometers. When the dimensions of microstructures are much larger than the width of the domain wall, the following types of magnetic structures are observed: the Landau structure, the cross-tie structure, the diamond structure, and the concertina structure. When the dimensions are comparable to the width of the domain wall, the following types are observed: the vortex, hyperbolic vortex, flower state, C state, and S state. For the manufacture of epitaxial magnetic micro and nanostructures, we use the method of pulsed laser deposition of films in ultra-high vacuum on single crystal sapphire substrate R and A planes with the seed layer of molybdenum 5 nanometers thick. Magnetic elements are manufactured from epitaxially grown films using subtractive technology. An aluminum mask of the desired shape is fabricated on the film surface using electronic lithography, followed by ion etching, followed by removal of the mask residues with wet chemistry. In this way, arrays of elements duplicated each other were fabricated from ferrum 011 films grown on the A-plane of sapphire. These elements were rectangles 0.5 to 32 micrometers long and 0.5 to 4 micrometers wide, and crosses. The axis of the long rectangle were oriented parallel to the z-axis of magnetization or perpendicular to it. The structure of striped domains with magnetization along the z-axis is clearly visible. The plot shows the dependence of the width of the stripe domain and the width of the vertex on the width of the rectangle. Solid lines are power law approximation of the results. For comparison, polycrystalline structures were fabricated by the lift-off method from the ferrum films grown on silicon oxide in order to avoid oriented film growth. It can be seen in this case the magnetic structure is irregular. To study the magnetic structure of magnetic elements, we use the method of magnetic force microscopy, MFM. This is a variation of the scanning probe microscopy technique in which the probe is a tip covered with a ferromagnetic material that vibrates over a sample. The gradient of magnetic force acting on the tip is measured, which also depends on the material of the tip covering. Therefore, the interpretation of the magnetic contrast can be ambiguous. A desirable approach is to experimentally determine the force acting on the probe and numerically solve the inverse problem to find the magnetic distribution. Another approach is the micromagnetic modeling of the magnetic structures using the Landau-Lifshitz-Gilbert equation and simulation of the MFM contrast based on the obtained magnetic structures and comparison with the experiment 1. That is the direct problem. Using the data of magnetic force microscopy and micromagnetic modeling, diagrams of micromagnetic states were constructed in the coordinates of the structure width and the aspect ratio. For rectangular elements perpendicular to the easy axis of magnetization with decreasing width, the magnetic structure of in the form of the stripe domains transform into the diamond structure and vertices. For elements located along the easy axis, there are also the Landau structures and quasi-single domain states. For rectangles oriented at an angle of 35 degrees to the easy axis of magnetization, there is a stripe domain structure and a more complex structure, which we called a centipede, which is an insect with many legs. The interpretation of such structure using micromagnetic modeling is shown in the figure. Above is the experimental results and below the calculation results. Arrows indicate the local direction of magnetization. The color shows the simulated magnetic force microscopy image. In the same way, we studied elements made of iron 001 films grown on the airplane of the subsphere. In this case, there are two easy axes of magnetization perpendicular to each other in the film plane. The elements oriented parallel to the easy axis depending of the width and the aspect ratio. There are two types of magnetic states: diamond structure and the Landau structure. With an increase in the aspect ratio, the diamond structure transforms into the Landau structures when the elements are oriented and at an angle of 45 degrees to the easy axis with large aspect ratios. Concertina structure is observed, and with small aspect ratio, a vortex, hyperbolic vortex, is observed. The diagrams of micromagnetic states are also presented. The experimental magnetic force microscopy image and the result of micromagnetic calculation of the elements of in the shape of the cross oriented at an angle of 45 degrees to the easy axis of magnetization are presented. The magnetic structure in the central part of the cross is rather complex. A rectangular structure, a regular structure with parallel domain walls and given period of the repetition can be obtained by specifying the shape of the magnetic element using the electron lithography technique. The magnetic structure of ferromagnetic elements can be influenced by the actions of pulses of spin polarized current. In this experiment, the direction of the magnetization of 4 domains in the square changes depending on which path the current is applied to, first pass or second pass. Figures A and B show the distribution of magnetization, and figures C and D show the distribution of the current density. To reverse the magnetization of such structures, Current alone is not enough, but together with the current pulse and external magnetic field is also supplied, always directed in one direction. The magnetic state into which the structure will switch is determined by the current. The effect of anisotropic magnetic resistance has been known for the first time. It consists in the fact that the resistance of a ferromagnetic metal depends on the angle between the current flowing through it and the magnetization of the sample, which is determined by the external magnetic field. The first model of this effect it was proposed by Sir Neville Mott in 1930s and was subsequently refined by John Smith and later by other researchers, in particular Robert Potter and Albert Fair. The model is that since the probability of the electron scattering with spin flip is small, then two channels of electric current can be considered, spin up and spin down channels, each having its own resistance. A mixing between channels is possible due to the spin-orbit interaction. In this case, the inverse SD scattering time depends on the angle of the at which the S electron approaches to the magnetic moment of the D electron. Since the wave function of the latter is anisotropic. The effect essentially depends on the density of these states at the Fermi level. For nickel, where the density of the states with spin down is significantly greater than spin up, it is large. And for iron, when the differ little, this effect is small. Ballistic spin transport is a new direction in the development of spintronics. To implement this transport, it is necessary to have large electron mean-free paths. The slide shows the results of measurements of the giant band magnetoresistive effect in planar nanostructures based on epitaxial nickel films. The band resistant measurement circuit is shown in the figure. At room temperature, the mean free path is small, about 20 nanometers, and electrons move in the diffuse mode. In this case, the potential of contact 2 is greater than on contact 3. At the temperature of liquid helium, the mean free path of electrons is about 600 nanometers, which exceeds the street width, namely 400 nanometers. In this case, the electrons move in ballistic mode and fly into contact 3. The potential at contact 2 in this case is less than at contact 3. A hysteresis look like curve is seen on the curve on the longitudinal band magnetic resistance and 4.2 Kelvin. The magnetic resistance effect is over 260%. The transverse band magnetic resistance has two minima, and the effect size is more than 250%. At room temperature, the band resistance is positive, and the magnitude of effect is not more than few percent. For comparison, the curve of the anisotropic magnetic resistance of the bridge at 4.2 Kelvin is shown. It is seen that the effect is small, thus ballistic enhances the small effect itself. It is known that the phenomenon of exchange bias of the hysteresis loop takes place in ferromagnet and antiferromagnet structures. Currently, this phenomenon is used to fix the reference layer in spin valves. There are many theoretical models of this effect, which consider the interfaces between the ferromagnet and antiferromagnet as uncompensated when the antiferromagnet layers adjacent to ferromagnet the spins are ordered ferromagnetically, or as compensated when they are ordered antiferromagnetically. And in this case, the spins of the ferromagnet align perpendicular to the spins of antiferromagnet. The quality of the interface affects the magnitude of the effect, and which increases with the epitaxial growth of the FM-AFM layers. We have grown and studied two-layer ferrum-manganese films. The magnetic force microscopy measurements showed that when the ferrum-manganese layer is grown on the top of ferrum layer, the square microstructures have a regular magnetic structure. When the ferrum-manganese film is on the bottom, the magnetic structure is less regular. The latter can be explained by the lower epitaxial quality of the sample due to the large lattice mismatch of the ferrum and ferrum-manganese layer. Magneto-resistive measurements of bridging structures shows that the ferrum-manganese ferrum-molybdenum earth sapphire layer exhibit exchange bias along the ferrum 0, 1, 0 crystallographic direction, while ferrum-manganese molybdenum earth sapphire films do not. It is known that the magnetic state of the rectangular microstructures ferrum 001 with aspect ratio 1/2 has a diamond state. In zero magnetic field, the area of the central domain is equal to 1/4 of the area of the entire rectangle. If there is a built-in exchange field directed along magnetization of the central domain will be expanded. The plots of the normalized central domain area of rectangles corresponding to figures, these figures are presented respectively. An approximation of the experimental data for the normalized area of the central domain gives an exchange bias about 35 Gauss. When the built-in exchange field is perpendicular to the external magnetic field, there is no exchange bias effect, and this is confirmed by the electric measurements. One of the possible methods for generating terahertz radiation in magnetic nanostructures was proposed In the works of Professor Zilberman, let us consider ferromagnet-antiferromagnet interface through which a spin polarized electric current flows. The current flows along the x direction, perpendicular to the interface, and spin is polarized along the z-axis, which is specified by the magnetization vector in the ferromagnet. The vectors of magnetic moments in the antiferromagnet sublattices and the initial moment are directed in the y direction, as shown in the figure. When the current flows, due to the exchange interaction of electrons carrying current with electrons of atoms of the magnetic sublattices, the magnetic moments of the sublattices are skewed along the z-axis, and the precession occurs with frequency of terahertz range, which can lead to terahertz radiation. To study the proposed effect, ion films of ferromagnetic metals were ground of heated substrates of airplane of sapphire with in situ control of the electrical resistance of the film. The observed dependence of the resistance on time is a relatively slow decrease, ending in a sharp drop corresponding to the percolation transition. To prepare films consisting of ions, the deposition process was interrupted before the onset of the percolation transition. The morphology of the ground ion films was studied ex situ by scanning electron microscopy and atomic force microscopy. Atomic force microscopy and magnetic force microscopy images of ion islands covered with nickel ore field in an external magnetic field are presented. The islands are magnetically coupled, since the size of the magnetic features exceeds the size of the island. The emission spectra of ferromanganese island metamaterial in the far infrared range were investigated by passing a current through it. The figure shows the emission spectra different current values normalized to the spectra at zero current. It is seen that the spectra contain several peaks. The magnitude of each increases with increasing current. Perhaps they are associated with the action of spin polarized current on sublattices of the antiferromagnet. The use of half metals implying 100% spin polarization at the Fermi layers and the Fermi level can potentially increase the spin polarized current density in structures with such materials, which should lead to the significant increase in the magnetic-resistive effects and possible generation of terahertz radiation. It is known that some of the Heisler alloys, for example, cobalt-2 ferrum aluminum or cobalt-2 ferrum silicon, have the property of half metals. A complete Heisler alloy has the chemical structures X2, Y, Z, where X and Y are transition elements and Z and P elements. The direct full Heisler alloys has a crystal structure L21 consisting of 4 interpenetrating FCC lattices, and as a consequence has 225 symmetry group. Films of cobalt-2 ferroaluminum Kessler alloy were grown from a target made of this material by pulsed laser deposition in ultra-high vacuum on a plane of subsphere at temperature of 270 degrees centigrade with a seed layer of tungsten. The elemental composition of the films were investigated, and it was found that the used method tolerates it quite well. Microstructures were fabricated from the films, and their magnetic structure was investigated by magnetic force microscopy. It was found that there is a regular structure and there is a easy axis of magnetization, the direction on which coincides with the direction of that for iron films grown on this subsphere plane. Investigation of the resistance of the films in magnetic field lying in the plane of the film and directed parallel and perpendicular to the longitudinal axis of the bridge gives the magnetic field dependence resistance characteristic to anisotropic magnetic resistance. Based on the results of measurements of the magnetoresistant curves, the angular dependence of the coercive field was plotted. As can be seen from the figure for the coercive field obtained films, there is only the one preferred directions. That is, there is a uniaxial magnetic anisotropy. In addition, for some films, the inverse dependence of the transverse and longitudinal magnetization was found, which indicates the realization of the state of half metal in such film. Recently, a new theoretical model has been developed that analyzes the effect of anisotropic magnetic resistance for various magnetic materials. In the framework of the new model, SD scattering electrons, which is the cause of the anisotropic magnetic resistance of half metals, occurs mainly from the S spin-up state to D spin-up state, or from S spin-down state to D spin-down state, which leads to negative sign of the effect of magnetic resistance. In the case of the positive value of the anisotropic magnetic resistance in conventional ferromagnets, the SD scattering with spin flip prevails. The angular dependence of anisotropic magnetic resistance effect has the form, the such form, where phi is the angle between the direction of the current and the magnetization of the sample. I is the index of the crystallographic direction along which the current flows. In contrast to conventional ferromagnetic metals, the decomposition coefficients C in half metals depend significantly on crystallographic direction. Thus, according to theoretical context, measurements of the magnetic resistance provide information of the state of half metal in the film under study without any additional research and manipulation associated with microstructuring. A comparison of cobalt-2 ferrum aluminum and cobalt-2 ferrum silicon films grown at a substrate temperature of 280 degrees centigrade with molybdenum seed layer has been carried out. Films of both materials show inverse magnetic resistance, which indicates that they are half metallic. When the films are annealed, this property is lost. The figure shows the dependence on the coercive field on the angle between the bridge axis and the external magnetic field before annealing, after annealing, and after annealing at high temperature. It is seen that magnetic anisotropy is lost, which is apparently associated with the precipitation of another phase. Now, conclusion. Arrays of elements were fabricated from ferrum on sapphire films by past laser deposition of films in ultra-high vacuum on single crystalline sapphire substrate, R and A planes, with the molybdenum seed layers. For elements made of ferrum 011 film in the form of rectangles oriented perpendicular to the z-axis, the structure of striped dolmens with magnetization along the z-axis was found. For elements from polycrystalline ferrum films grown on silicon oxide, the magnetic structure is irregular. Using the data of magnetic force microscopy and micromagnetic modeling, the micromagnetic state of rectangular elements from ferrum 011 and ferrum 001 films were found, and their diagrams were plotted in the coordinates of the structure with an aspect ratio. The magnetic structure of a ferromagnetic element in the form of a square made of ferrum 001 film was switched by the action of pulses of spin polarized current in the presence of an external magnetic field, always directed in one direction. The magnetic state into which the element switches is determined by the current. The effect on giant band magnetic resistance was discovered in planar structures based on the epitaxial nickel films. At the temperature of liquid helium, the mean free path of electrons in such films is about 600 nanometers, which exceeds the width of the stripe in the measured nanostructures. Electrons move in ballistic mode, and the magnetic resistance effect is over 260%. In the two-layer ferromanganese films, when the ferromanganese layer is grown on the top of the ferrum layer, the exchange bias effect is found to be about 35 Gauss. In the case of growing ferrum layer on the top of ferromanganese layer, there is no exchange bias effect. A technology has been developed for growing iron films of ferromagnetic metals on heated substrate of the airplane of sapphire with in situ control of electrical resistance of the film. The emission spectra of the island metamaterial of ferromanganese in the far infrared range are investigated when the current is passed through it. The spectra contains several peaks, the magnitude of which increases with the increasing current. Perhaps they are associated with the action of spin polarized current on the sublattices of the antiferromagnet. Films of cobalt-2 ferrum aluminum and cobalt-2 ferrum silicon Heisler alloys were grown from targets made on these materials by post-laser deposition in ultra-high vacuum on the A-plane of subsphere. The advantage of the method used is fairly good transfer of the target elemental composition of the film. The film have one easy axis of magnetization in the plane. For some films, an inverse dependence of the transverse and longitudinal magnetic resistance was found, which indicates the state of how metal is realized in such films. Thank you very much.
Thank you, Professor Fomin, for a very good talk. Now the session is open for short questions, quick questions. Anyone in the, from the participants who wants to have a question? Okay, if there are no any more questions, we'll move to the another section because we are running short of time. So now the session will pass to Dr. Suraj Kumar Singh. And once again, I would like to thank Professor Fomin. And from the participants, if you have any questions regarding Professor Fomin's research work, you can contact him via email. I hope there will be no problem if I share your email with the participants. Yes, Professor Fomin. Can I share your email to the participant? Okay, now I will close this session and pass to Dr. Suraj. Thank you. Sir Suraj, are you here?
Oh, hello. Dr. Suraj is having some technical issue. I think he'll be joining us soon.
I think I'm now online.
Dr. Suraj is now ready. Yeah, please go ahead, Suraj.
Yes. So we are in the third session of this first day, and we are now having two speakers, and the first speaker is Dr. Tista Prasad Joshi. He is a scientist at the Nepal Academy of Science and Technology, and Dr. Joshi is having more than 18 years of research experience, and his research is focused on water quality and purification using absorption technology. Dr. Joshi has got many awards and fellowships, like OWSD Elsevier Foundation Award in Biological Sciences, 2019, UNESCO OWSD Early Career Fellowship, 2019, UCAS Excellent International Student Award, 2017, and many more. And he was awarded with the President of Nepal, Right of Honorable President of Nepal for achievement in his PhD research as well. So now we welcome Dr. Joshi to deliver his speech. Please go ahead, Doctor.
Thank you, Dr. Suraj Kumar, for the nice introduction. Thank you, organizing committee, for inviting me as a speaker in this conference, International Conference on Material Science and Applied Physics, and wishing all the best for the successful completion of the conference. Now I'm going to share my screen. Yes. Okay. The title of my presentation is Use of Adsorbent for Organic Arsenic Remediation. And now these are my, yes? Is it audible or my slide is clear?
Yeah, ma'am. It's well and
yes. These are my outline of the presentation, and within the time frame, I try to finish all the presentation. And now, okay, I'm basically talk on the organic arsenic, which is aromatic organic arsenic, and aromatic organic arsenic compounds such as para-arsenilic acid, roxazurin. Here, this is the structure of the para-arsenilic acid, which have been extensively applied as a feed additive for poultry to treat a crocodile intestinal parasites, and which helps to enhance the feed efficiency, promote the rapid growth, and to improve the meat pigmentation of the broiler chicken. Most of the organic arsenic compounds are excreted chemically unchanged in the manner which is widely used in the agricultural application, then enter the environment through the poultry litter. Furthermore, it has been reported that the abiotic and biotic transformation of aromatic organoarsenic compound under anaerobic condition contribute to the release of the more toxic arsenic, which is highly mobile, and during the transformation process, inorganic arsenic makes its way through the environment into surface and groundwater sources. Arsenic can also be absorbed by vegetables from the soil and enter the food web and ultimately transferred to the human being. For all these reasons, it is crucial to remove the aromatic organic arsenic compound from the poultry manure to control the organic arsenic transformation and entry into the environment. Therefore, adsorption technology is applied here in this research, and adsorption exhibits the advantages of simple operation, high efficiency, low cost, and is particularly valuable for organic arsenic removal. Many adsorbents have been developed for the removal of inorganic arsenic. Therefore, it is highly attractive technique. Here are some of the adsorbent here I have written here, given here in this slide, and a contaminant attached to the outer surface of the solid surface is called an adsorbate, and the underlying solid surface is called an adsorbent. Adsorbate, here I use the para-arsenic acid as an adsorbate as a pollutant. And the adsorption capacity of an adsorbent is determined by several parameters such as temperature, pH, surface characteristics of the adsorbent, and the properties of the adsorbate. Selection of an appropriate adsorbent with a suitable capability is a significant step in designing water treatment process. And in my research work, I have used prepared several adsorbent, FMBO, FUH, MnO2, FEMN framework, cubic FUHC, and which was published in these papers also. Here, basically, I'm talking about the manganese oxide. And how to prepare manganese oxide in the laboratory. I have used a potassium permanganate manganese sulfate for preparation of the manganese oxide. Here is the process applied for the preparation of the manganese oxide, and which was prepared in the laboratory, and it was centrifuged, lyophilized, dried, sieved, and preserved, and the particle was dried in the lyophilization and crushed into the fine powders, and the size
less than 100 micrometer and preserved in the vacuum desiccators, and then was ready for the adsorption study. There are several techniques were applied for the structural characterization of the adsorbent. Here, XRD was used to investigate the surface characteristic, identify the phase composition, crystal structure of prepared adsorbent, manganese oxide, and Brunner M.A. Taylor was also used to investigate the textural characteristic, which helped to determine the porosity and specific surface area. Likewise, scanning electron microscope was also used to produce the high resolution image of a sample surface to examine the shape and structure of the prepared adsorbent. And zeta potential machine equipment was used to determine the change in the surface charge. Therefore, several techniques were used for the morphological and microstructural characterization of the adsorbent, which has provided an important insight into the structural property of the adsorbent. In order to understand the adsorption behavior and adsorbent were characterized systematically. The systematic characterization of adsorbent may provide important insight into the understanding of the adsorption behavior and mechanism. The specific surface area of the manganese oxide was found to be 93.24 meters square per gram. Pore volume was observed 0.34, and the pore size was found to be 14.58. And this specific surface area also showed that it might be the amorphous. And the XRD result indicated that no obvious crystalline peak was detected. This revealed that this manganese oxide was amorphous. And two predominant peaks, 37 degrees centigrade and 66 degrees centigrade, were observed. And it might be due to the formation of the delta manganese oxide. It was supported by the many other previous literatures also. The zeta potential of manganese oxide decreased from minus 10.8 to 57.4 MB when pH increased from 2 to 8. The isoelectric point was about 2. And the SEM image demonstrated that the scanning electronic microscopic image demonstrated that an aggregated nanoparticle formed with a rough surface micrometer-sized morphology. Here, I have chosen this para-arsenilic acid as a major adsorbate, and structurally para arsenic acid is a type of phenyl arsenic acid and molecule with substituted functional group where an amine group is added to phenyl arsenic PA molecule at the para position to form a para-arsenilic acid. And aniline is a part of an important family of industrial chemical applied in the synthesis of several synthetic organic compounds, such as pesticide, dyestuff, pharmaceutical product, and so on. Here in this research, we describe our investigation on the behavior of the individual compound para-arsenic, phenyl arsenic acid, and aniline, the analysis of which could provide in-depth mechanistic understanding of PASA transformative pathway. And this work was published in the Water Research. And manganese oxide is generally applied to remove the toxic compound in the environment because of the strong oxidizing property and has adsorptive capability. Additionally, manganese oxide could remove several organic pollutants such as aromatic amine, aniline, phenol, antibacterial agent, and endocrine disruptor. The objective of this study was to investigate the adsorptive and oxidative property of the manganese oxide for the removal of the para-arsenic acid under the different pH condition. Here it is shown in the figure adsorption kinetics. In this graph, illustrate the adsorption kinetic of para-arsenic acid, phenyl arsenic acid, and aniline onto manganese dioxide under the different pH condition 4 to 9. This is 4, 5, 4, 6, 7, and 9 over 24 hours. Initially, the adsorption was so rapid in all these pollutant. and the removal rate was also higher. However, it slowed down considerably later on. The absorption of aniline on MnO2 was faster than PASA and para-arsenic acid. And the removal rate was also higher in aniline in comparison to PASA and the phenyl arsenic acid. And adsorption performance decreases when the pH increases from the pH 4 to 9. And in the 9 pH, the adsorption was significantly decreased. And all these experimental data show that pH played an important influential role in the adsorption of para-arsenic acid, phenyl arsenic acid, and aniline on manganese oxide, following the order pH 4, 6, 7.5, and pH 9. To understand the adsorption kinetic behavior, various models such as CDO first order, CDO second order model, and aerobic model was applied for the fitting the kinetic data. And these are some of the experimental conditions which was given here also. And another experiment was also conducted to find out the oxidation process. The release of the manganese resulting from the oxidation was also observed after the adsorption of PASA, PA, and aniline on MnO2 after over a wide range of pH. In agreement with the above oxidation result, manganese concentration was 17.5 milligram per liter for aniline, whereas for PASA 9 milligram, 8 milligram per liter, and in the PA the oxidation rate was also slow, and the manganese release is also very low. This is 1.2 milligram per liter. Manganese was released into the solution as a result of the manganese oxide reduction through the oxidation of ASA and aniline. And this graph illustrates the change in the UV spectra during the adsorption of PASA, PA, and aniline onto the manganese oxide over a wide pH range 4, 6, 7.5, and 9. The shape of UV visible spectra varied with pH after the reaction of PASA, PA, and aniline with MnO2, indicating the occurrence of structural change from the formation of new product is due to the oxidation of PASA and aniline. After the reaction of PASA with MnO2 at pH 4, the absorbance band at 254 nanometer decreased and shifted to 245 nanometer over the course of the reaction, indicating the presence of new product benzoquinone. However, the PA spectra did not vary significantly over a wide range of pH. A similar UV spectrum 10 was observed in the case of aniline, where the UV visible spectrum showed a change after the adsorption of aniline on MnO2. At pH 4, a peak that appeared at 245 assigned to the benzoquinone was also observed in the aniline spectrum. Furthermore, a new broad peak appeared between 300 nanometer and 480 nanometer, indicating the formation of the new product, azobenzene. And change in UV visible spectra after the reaction of PA and aniline at different pH was given in this figure. And the sample was taken in different time interval from 0 to 24 hours time. And the characterization of oxidation intermediate of ASA on manganese oxide over a wide range of pH was carried out via the ultra performance liquid chromatography ICP mass. Identification of arsenic species was confirmed based on the reaction time, retention time, PASA, PA, and converted into this arsenic 3, arsenic 5. And PASA was converted into arsenic 3, then it was further rapidly oxidized into arsenic 5, indicating that the adsorbed ASA could be oxidized to arsenic 5 by manganese oxide within 3 hours time period. The release of low concentration of arsenic 5 at pH 6 and arsenic 3 and 5 at pH 7.5 was observed, suggesting the slow oxidation of PASA on MnO2 respectively. However, the oxidative and adsorptive rate was too low to observe at pH 9. And here in the adsorption and oxidation of aniline also, in the first within a few minutes, it was immediately transformed and formation of the new product here. And to support all this, and this is also same result from the same experiment, ICP-MAS UPLC. Here is formation of the new product arsenic 5 at pH 4, and whereas in arsenic at pH 6 the very little amount, but in pH 9 there is no formation of any new product. And to support the hypothesis, complementary experiment using HPLC were further conducted to determine the adsorptive and oxidative behavior of PSA on MnO2, which confirmed the complete oxidation of PSA at pH 4. However, the oxidation of PSA at pH 6, 7.5, and 9 did not change appreciably, with the degradation of transformation of aniline after the adsorption on MnO2 was investigated using HPLC. And the two new peak were observed at pH 4, indicating the formation of the new product. The combined result of UV visible spectra and HPLC confirmed that the intermediate product were azobenzene and benzoquinine. Here, this result from this UPLC Q-TOF determined that the new product is the benzoquinine and the azophenyl arsenic acid. And adsorption and oxidation properties mechanism was done by using the FTIR and XPS. Here in FTIR, spectra of adsorbent before and after adsorption were measured. For the PSA, for PA, and aniline. The peak at 1590 centimeter, 1590 per centimeter and 1510 centimeter were attributed to nitrogen-nitrogen stretching in the quinine ring and the carbon-carbon stretching vibration of the benzenoid ring, respectively, resulting from the aromatic amine group in PSA and aniline moiety. Additionally, there appeared a small peak at 846 here, 843. This is PSA here in 846 for both in 846 and here 890 for both samples. They indicated the presence of stretching vibration of arsenic bond of PSA. The newly appeared peak at 1385 here corresponded to the nitrogen-nitrogen stretching vibration and might be due to the formation of the azophenyl arsenic acid, which is the product of this compound. Here in the X-ray photoelectron spectroscopy is an effective tool for exploring the elemental composition and oxidation state of surface chemical environment. The surface properties of adsorbent before and after organoarsenic adsorption were analyzing using the XPS. And XPS spectra provided the important information on the mechanism involved in PSA, phenyl arsenic acid, and aniline, respectively, and reacted with manganese oxide. Additionally, XPS spectra of nitrogen 1s showed another peak at 399 if related to the nitrogen of the azo functionality group of ASA and aniline after the reaction, which was supported by the above experimental result, UV spectra of PSA and aniline after the reaction with MnO2 as well as UPLC Q-TOF mass and FTIR respectively. Thus, based on all the combination of the identified intermediate in a solution and the final product on the surface, a removal mechanism for para-arsenic acid on MnO2, this is para-arsenic acid and MnO2 is proposed. And during the initial stage of the reaction, the PSA removal mechanism was adsorption. The monodentate complex was formed on the surface of the manganese 4 by the removal of H+, which was given in the step one. As the reaction process continued, a PSA oxidation capacity was significantly improved through the transfer of the one electron. from PSA on manganese oxide surface to produce a PSA radical intermediate. Additionally, the reductive dissolution of manganese oxide and reabsorption of manganese 2 represented significantly. The radical intermediate could be further hydrolyzed to form the new product benzoquinone, and indicating the effective coupling of the radical intermediate and the hydrolysis reaction, resulting in the formation of the new product here in the step 2. Similarly, the oxidation of PSA radical caused it to be cleaved to form arsenite and then oxidized into arsenate with the release of manganese in the solution, indicating the heterogeneous oxidation process. Moreover, PSA radical intermediate was again transformed through the radical to radical coupling to form a new product, azophenolic arsenic acid, which is given in the step 3 process. And this is the summary of this product, and which was experimentally done by the Icmsap UPLC. Here also you can see the PSA and the formation of the product, intermediate 1, 2, and also the product 2nd. And the conclusion of this research is the adsorption kinetic experiment revealed that the removal rate of PSA, PA, and aniline by adsorption were strongly pH dependent. The oxidative and adsorptive properties of PSA, PA, and aniline onto the manganese oxide were examined, thereby recognizing protonated amide as the major functional group affecting the transformation pathway. The result derived on the basis of changes in UV spectra and spectroscopy study gave a plausible explanation for the formation of the new oxidation product, arsenate, benzoquinone, and azophenol arsenic acid. Now I'm going to talk about some of my ongoing project in my academy, Nepal Academy of Science and Technology, which is focused on the drinking water quality research and service. Here I'm working on the different aspect like a service oriented. My environment and climate study laboratory give a service to the general public since 2001, and the other part is a research oriented. We have monitored the different water quality sources like processed water, wastewater, river water, groundwater, and so on. And recently we have also worked on the water purification technique by using adsorption technology, and the major pollutant are organic arsenic. And for this, we have prepared numerous kinds of the number of the adsorbent and adsorption removal mechanism and removal efficiency is going on. And likewise, microplastic in urban lake is also detected. And another very important process is we are working on public awareness for safe drinking water and sanitation practices from lab to land oriented. They all are the research student, and she is my PhD student. She is working on microplastic, and other students are working in different aspects. He's working in wastewater, he's working in antibiotic, in the pharmaceutical wastewater. They are working on the water quality services as well as analysis. And I have also got one grant from the UNESCO Organization for Women in Science for the Developing World Early Career Fellowship, where I have used the monomethyl arsenic and the DMA, and now working on the DMA and arsenite and arsenic. And my students, my researchers is preparing numerous kinds of the adsorbent and working it. They are working very hard to get the good result. And also another important thing is the capacity building. And from the grant, I have purchased the one very useful equipment for the characterization of the material, which is data potential. And we are providing the services to the many public institutions, private institutions, and universities. Here, I also got this machine as a support, and I am also supporting my others researcher in the free of cost also. And she is my research assistant. She is working also under this project, and she is doing on the material science. And for the lab to land process, we have a scientific village program. Recently, I went to the one of the remote area of the Gorkha Siranchik, where I conducted the interaction program about the water quality, also demonstrating water analysis, and also collecting a water sample from the Siranchik villages. And also we have also installed established a laboratory. And here in the Science Street Fair, I'm demonstrating the material observant to the Deputy Prime Minister, at that time Deputy Prime Minister. And this is also another interesting program conducted by the Nepal Academy of Sciences, very remote area. And we have also conducted every year Science Teachers program. Likewise, we did so many activities as a lab to land program. And thank you. This is my academy, and this is our research laboratory. Thank you so much. Thank you, everyone, for giving this opportunity to say something about my research and also my recent research activities. Thank you so much.
Okay. Thank you, Dr. Joshi. And if anybody has any comments or any queries, then please go ahead. So if there is any comments and queries, please. And if not, let us thank Dr. Joshi for the nice presentation. And water is very important to all of us, and the work that you are taking up, I hope will be contributing in providing water without contamination. So thank you and congratulations. So thank you, ma'am.
Thank you. Thank you.
Then we'll take up to the second speech for today. So the second speaker is Dr. Ranjit Thomas.
Yeah, am I audible?
Okay, so now
Am I audible?
Yes, yes.
Yeah, fine.
So we have now Dr. Ranjit Kumar, and he's a assistant professor stage 3 at the Department of Chemistry, St. Bartman's College, Mahatma Gandhi University, Kerala. And he has a research experience of more than 8 years, and he is interested in the theoretical organic chemistry, chemical physics, solvation studies as his research interest. And Dr. Ranjit has more than 75 publications, and he is a member in the editorial board, BMC Chemistry, Springer Nature Group, and a guest editor, Frontiers of Chemistry, special issue. And he is also a member in the many professional bodies like Fellow Indian Chemical Society and many other professional bodies. So now let us welcome Dr. Thomas to deliver his speech. So please go ahead.
Thank you, Professor Suraj Kumar. My screen is visible or not? Can you see my screen?
Yes, yes, it's visible.
Thank you. Let me first of all thank Dr. Professor Suraj Kumar, and also thank my dear friend Divya Rai for inviting me for this conference. I know that it's a conference for physicists, and but I work closely with more physics guys than chemistry guys, so I'm very happy to give a small talk on the theoretical and computational tools that we use for the study of physics and chemistry of organic systems. And I comes from St. Bartman's College. It's actually one of the oldest college in state of Kerala, and it's an NAC accredited A+ college. And I am one of the faculty of the Department of Chemistry. You can see Department of Chemistry. Here is the ground floor belongs to Department of Chemistry. My topic I'll be discussing not only my research, I will just giving you an introduction to the basic theoretical chemistry and some of the basic theoretical physics. And later I will go to one of the area of my interest called solvation. And after that, I will discuss a problem that we just solved. And let me tell you, first of all, what is called solvation. As per the IPC recent compendium, solvation is any type of stabilizing interaction of a solute or with a solvent. It can be done by many types of interactive force like electrostatic force or van der Waals force, and as well as chemically or more specifically effects like hydrogen bonds. And let me first of all tell you the importance of the solvation effects. You can see that this is a beriberi molecule. It's an alkaloid molecule. You can see that here, if it is the UV spectra of the molecule, it's very definite that the values lambda max actually varies with different solvents. And also, it is very seen that the fluorescence property also varies with the different solvents. And this may be due to basically the a difference in the interaction between the energy levels and the solvent molecules, and therefore the modeling of solvation effects in UV spectra is very important. Not only in UV spectra but all in all of the topics very important. This is again a solvative conformism. Solvative conformism means the difference of coloring in different types of solvent. You can see that this type of this is a compound and is an naphthalene dicarboxamide. You can see that the color of the system varied significantly with different solvents. So solvents impart very important effect on that. And let me just first of all talk about what is called computational physics or computational chemistry. It's a chemistry in the computer or physics in the computer instead of in the lab. And due to the dramatic increase in the speed of the computers and the availability of efficient quantum chemical algorithms, we have modernized the system, and we can see that we can do a lot of computational chemistry experiments in day-to-day life, even with small laptops and workstations. And there are basically 4 different types of quantum methods that we employ computationally. One is the molecular mechanics methods based on force fields, then semi-empirical methods, ab initio methods, and density function theory methods. You can see that the first one is molecular mechanics method. It uses the classical Newtonian physics. It assumes Hooke's law. You are familiar with the energy of stretching of a bond is proportional to the displacement from the mean position, and E is equal to Ks into I minus I0 raised to 2, where Ks is spin constant. And this is actually based on classical physics. It's very easy to perform and it's very simple. But we can get some empirically derived relationship between energy and bond angles, dihedral angles, and distance, etc. And the problem with this is that it ignores the electrons and the effects of the pi electrons. And it's very simple, but gives some reasonable but limited results for every system that we consider. And the total energy is considered to be steric energy. It is sum of the various artificial energy components depending on the program and not on the real measurable energy. That's why the use of force fields are very important. The choice of force fields are also very important here. And the enthalpy of formation and dipole moment could be measured to some extent by using molecular mechanics methods. The different molecular mechanics force fields like MM2, MMX, etc. And the common force fields we employ is Amber, is a very famous force field, and OPLS force field by Johansson. It is used in the famous Desmond software for dynamic simulations. And also BioPlus is there, and a lot of others are there. And you know that the coding field is very strong now, and these days every year or so we can come with the new force fields. The next one is semi-empirical molecular theory, and this employs the Schrödinger equation to estimate the energy of system as a function of geometry and electronic distribution. And the problem with the semi-empirical method is that the actual solution is the complete solution of Schrödinger equation. But here the problem is that we use some empirically derived, not theoretical data, like the bond length of the common bonds, like HF bond, carbon-carbon single bond, carbon-carbon multiple double bond, triple bond, etc. And it also takes the experimental data for the energy of electron, mass of electron, etc. By using this method, we can calculate the energy. So, but it's not actually complete quantum mechanical method, but it's only semi-empirical, meaning we consider some of the experimental data also. There are a lot of applications for this method, and some of the methods we have Hooke's method, a very famous method for aromatic systems, Sinter methods, Minter methods, Inter methods, etc. And the latest we use AM1 methods and PM3 methods, mostly widely used, and this is available in most of the quantum mechanical softwares.
The next one is actually the most important one is the ab initio molecular theory. And here we solve completely the Schrödinger equation, not as a semi-empirical equation, but it's a complete solution. And we don't use actually approximations, only 2 data we use from experimental, but that's actually not 2 but 3, but one is velocity of light, and second one is mass of electron, and the third one is charge of electron. And this is actually a pure in relationship to theory. And if theory is correct, it should give you more accurate results. And the problem is that it takes, we are not using any experimental data. Therefore, it will take more CPU time because it will have to calculate all the data. And there are different variations of ab initio theory. The first one is the basic Hartree-Fock theory, where we imagine an electron experiences a sea of other electrons. And the next one is smaller closet perturbation theory. It includes some corrections like MB2, MB3, etc. There are configuration interaction methods, and we use a particular choice of basis sets like STO3G, like that. And there are different basis sets also available. And using the basis sets, we can, and the level of theory, we can get good results. So the 2 parts of the ab initio methods. So one is by the excitation hierarchy. We can get into CIS, configuration interaction singlet method, single doublet method, single double triplet method, etc. And also there's in excitation hierarchy, there's the MR-CASD method. And then is multi-configuration HF method. We got MC-SCF method and CASF method. The perturbation hierarchy, we have got MP2, molecular perturbation theory method. And in the perturbation hierarchy, we got Castep method and Castep method. And the thing is that all these methods leads to the full configurational interaction. That is where we expect very high results. And you can see the starting point of all these studies are shown in the equation, where we try to solve the H psi equal to E psi. If we vary the psi wave function, trial wave function, we get the variation method. And if we vary the Hamiltonian, we'll get the perturbation method. And psi is having enough physical significance. We take the square of psi, that will give the probability distribution. And this is a model chemistry. You can see that here we can use a minimal basis set, and if you use a lower ab initio method, we get less accurate results. And if you use a very higher sophisticated theory, and also if you use a very high basis set, and you can see that we get the full configuration interaction. That means the full exact solution of the Schrödinger equation. So again, the same representation. If you use infinitely high basis set, and if you use a very excitingly fully configurational theory level, we can get the exact solution to the problem that we are doing studies. And you can see that here, this is the full configuration interaction method, where we can get the error margin up to 0.1%. Semi-empirical method to get the accuracy is 10 kilocalorie per mole. But if you use full configurational interaction, we can reach the chemical accuracy of about 0.1 kilocalorie per mole, or more accurate than that. The next important thing is that there are debates that whether it is a quantum mechanical method or another method. It's called density functional theory. And in 1998, Walter Cohen got Nobel Prize in chemistry. He shared that with Popper, and Popper got for employing the the different methods of quantum mechanics to computational applications. And he was a pioneer in the starting member of the Gaussian software, even though Gaussian has expelled him later. Cohen is the one who developed the density functional theory. You can see 2 basic references where the Cohen and Cohenberg, they have introduced, and Sham also introduced the ideas of the density functional theory. It's considered to be one of the revolutionary theories. In 95 to 2000, density functional theory have used, even though it is first to developed to study the periodic systems for solids, basically for physics. But now chemistry people using the DFT theory a lot. And Agawajari, who is also a writer of Gaussian, in 2000 has said that he proposed that around the majority of the papers, not the majority, a vast majority of the papers published in computational chemistry uses the density functional theory. And in density functional theory, we do not calculate the wave function, but instead we calculate the electron probability density, psi, rho, x, y, and z. And this advantage is including less demanding computational effort because we don't want to calculate the wave function. And in some cases, better argument with the experimental data is also observed. There's a history of the development of the DFT equations. We don't have time, I don't want to discuss too much. And this is based on 2 important theories. The first theory by Cohenberg and Kohn. And the first theory is a downstate energy is unique functional of electron density. That means the functional. That means the energy density is a functional position, and that decides the energy. So it's called functional. And rho r represents the energy function. And theorem 2 says that the energy density that minimizes the energy of overall function is a true ground state density. That is an application of the variational theory. And we consider the function is a function of a function, and you can see the density reactivity term or the density function of electrons is a function of position and time. And if you ignore the time consideration, we'll be getting time independent differential theory, but this is not good in modeling time dependent phenomena like electronic excitation, UV spectra, and hence we make use of time there also. That's for time dependent density functional theory. Physicists have developed a lot in density functional theory, and nowadays many functionals in DFT also consider the density time dependency of the density functional theory also. And in this theory, there are different terms are involved. One is ion electron potential energy, ion potential energy, electron energy, and kinetic energy is there. And the most important one is exchange correlation energy. And it is the electronic correlation is the interaction between the electrons, the electronic structure of a quantum system. And the correlation energy is a measure of how much the movement of one electron is influenced by the other electrons in the medium. And these two terms are very difficult to calculate. And this, the idea how we calculate these two terms are very important in deciding the things. And in DFT, the first method approximation developed is local density functional approximation, and where there's approximations to the exchange correlation energy, and is a functional considered only as a function of the density functional theory. Okay, and there are many approximations also there, and it gave a new model called homogeneous electron gas model, and based on that, all the things came. Of course, it's basically good in predicting the properties of periodic systems like solids and to some extent liquids also. Next comes the generalized gradient approximations, where we consider, because in LDA approximates energy as a true energy density by the energy of a local constant density, but it is not good in the case of rapid changes. So to this, actually, we can use generalized gradient approximation of GGA. Okay, in GGA, what we do is that we consider a gradient of the density function also. That's why for gradient approximation. And can see this is the first level, LDA is the lowest level, then come GGA, and above that there is meta GGA, where we consider the functional also depends upon the kinetic energy density also. Later we got hybrid the GGA methods. This is very common and famous B3LYP functional is used based on that, and where we consider the functional as also have some contribution from the Hartree-Fock exchange energy also. It's called Jacob's ladder. You can see that from Earth to heaven is a chemical accuracy, and every step we can go by this method. We use LDA, less this thing is there, and if you go higher, we get PBA that we commonly use in physics are actually based on a GGA approximation. Okay, this is the list of the different functionals. And if you want to know which functional to use, there's a very nice report by Peratt and Crawford. It's the title is "Which function should I use?" You can go to this paper and find it, and I have taken this from this paper. These are the different types of density functionals. Okay, and commonly if you use that, if you take a list of functionals used, you can see that B3LYP is commonly used as one of the best functional, a popular functional. And again, still it is not away from any limitations. These are some of the basic limitations of the density functional theory. It's only a ground state theory. Eccentric state DFT is not that much strong. Only thing is that we have some time dependent density functional theory only, and universal functional is still unknown because we have to benchmark all the situation, and hydrogen atom is still a problem in density functional theory because it causes self-interaction correction. And there's no systematic way to improve the approximations like LDA, GGA, etc. Even though I have mentioned the Jacob's ladder before. Okay, and there's some of the popular quantum mechanical codes that we use for molecules, not for solids, as far as this is concerned. For me, as a chemist, I am satisfied with molecules. These are some of the common codes. These days I'm using Orca very commonly. Okay, it's a very good code, and I suggest you people to go through Orca if you want to do some DFT of molecules. And to account for solvation, I have mentioned that solvation is very important, and we need to have some models of solvation. And the first one, solvation model, there are three basic solvation models. One is implicit model, and next one is the explicit model, and the third one is the hybrid model. In the explicit solvent model is a urea molecule. You can see that water molecule, for example, the red dot represents water molecules. We consider the urea is present in real water molecules. So instead of one urea molecule, there will be also a lot of water molecules, maybe hundreds and thousands of water molecules in the real system. So we have to account for that also, and then you have to study. But the problem, this is very expensive because we have to consider a lot of atoms and molecules. But in the implicit solvation model, we don't consider any exact solvent molecules, but instead of that, we consider the molecules present in a solvation atmosphere or solvent atmosphere. And there's another model called the hybrid model, where it's a microsolvation model, in which we consider only some of the few water molecules near the molecule, and the rest in the bulk state we consider that it's a continuum model, or the implicit model is used. So we use the explicit model to some extent, and also the implicit model to the larger bulk system. That decreases the time of calculations. And this is the explicit model that we can see. The good thing is that we can calculate the free energy of solvation by stimulating the solvent-solute interaction in real time. The problem is that it's expensive. And this is an example of explicit quantum mechanical water model on the SN2 reaction. You can see that here water is going to attack this bond, but in reality, water is actually is also a solvent. And you can see that this one nucleophile can have interaction with several other water molecules and stop the speed of the attack of the OH, then which will explain the exact reason for this low reactivity of the chloromethane on water. Okay. And there is a hybrid solvation model of water, as I told you. This is the case, the above case, in which this is a system. We consider a few molecules, and this is in the quantum mechanical method. And the other area we consider that to be in the molecule. There is another way in which we can study quantum mechanically some of the nearest part of the molecule, and the other bulk system you can consider as actually as a molecular mechanics, because it takes less amount of time. It is called the hybrid QMMM method. In QMMM method, we consider the immediate phase of the layer of the system as QM method, and the other part we consider to be what is say the molecular mechanics way. Okay, so and there are different types of models also. If you do a molecular mechanics, there are different types of models also. These are some of the models. You can see that this model is considered only water molecule, and here there is another charge system is placed here, and I'll show next slide detail about this. And this is considered to be tetrahedral model. This is considered the most accurate, but takes a lot of time. And there are three-site model in which it's a water molecule. We consider three atoms, and three atoms of the water molecule is considered to interact with the solute. But in four-site model, we consider also a dummy atom M, where this M is actually accounts for the lone pair effects here, and dummy is there. And this is actually five-site model in which, along with the three model, we have got two lone pair of electrons, and lone pair effect is considerably exerted. And the six-site model, there is also a three here and the two lone pair, and also the dummy atom is also involved. The dummy atom is an electrostatic model. This dummy atom is used because the shape of the water molecule is cone-shaped molecule, because V-shaped molecule. If we don't place a dummy atom here, we can't account for the electrostatic field of the water molecule present here. And the implicit solvation model considers the solvation energy as the solvation and free energy for formation cavity, dispersion interaction, the electrostatic fault, and also the hydrogen bonding interaction. Okay, and this is the actual implicit formation model. You can see that here this is the solute that comes to solvent, and first of all, when the solute comes to the solvent, forms a shape here, and the shape starts developing a charge, and this charge will causes some perturbation in the solvent system, causes some charge here, and this charge causes some distribution locally, and later what happens, the solute polarizes in response to the solvent polarization. It is actually what is happening in the implicit solvation model. And this model differs in different aspects. The first important thing is that about shape. We can see that the shape is circular here, then it's called the Bond-Kirkwood method. If it is ellipsoidal, it is called the Onsager model, and it's a Van der Waals model here. And second one is the level of solute dispersion. Third one is effective dielectric medium description, and next one is cavity calculation method, and the last one is representation of the charge distribution. And this is the molecular topology of the molecule. Suppose this is the molecule, you can see that the whole surface of the molecule is not accessed by the solvent, and the solvent accessible surface shown by the blue color, it is called solvent access surface. It's also called the Leach-Richards molecular surface. And these are the atoms that's moving here, and this is the area, red color area, where solvent molecules cannot access. It is called the solvent excluded surface, or ACS, or the Connolly surface. And the dielectric medium description is very important because molecules will be having dielectric constant. And for that, there are different methods. The first one is the cavity calculation method. The next one is percentage of charge distribution and the polarizable condensation model. The different models to talk about that the cavity. One is the polarizable continuum model. And here in cavity, we consider the van der Waals spheres here, and we also consider the solvent access surface, and also we consider the iso density surface here. It's one of the different solvent models, and the one is IEF PCM model is called integral equation formalism model is there, as commonly used these days. I am a formal ardent user of that. Also, there's SMD model is also there. There's another model called conductor-like screening model called Cosmo model. It's actually not that much efficient as that of the PCM model because it is based on solvent access surface only, and also the electrostatic interactions are treated in a more approximate manner. And it's actually makes use of a big approximation for the polar solvents. And you can see that the accuracy is definitely higher for the PCM, and you can see this paper for benchmarking. Now, let me go to my research area. It is one of the research paper that we have got accepted recently. It is regarding the water as a hydrogen bond acceptor on the complexation with aliphatic thiols and aromatic thiols. And this is a study of the non-conventional hydrogen bonds. Okay, so hydrogen bond is defined as by IPC as the attractive interaction of hydrogen atom attached to a donor atom and an acceptor atom, and can be written as DNHAC. It is given by E. Arunan in the PR and Applied Chemistry Journal of IUPAC in 2011. And you can see that usually hydrogen bonds involving sulfur are generally regarded as weak classification of hydrogen bonds in comparison with the conventional hydrogen bond like NH, OH, OF, etc., because they consider strong. It's very weak because of the low electronegativity of the sulfur atom, and it plays very important role in the formation of the biological systems. So, but we say that we consider that even though it is like that, sulfur is non-normally considered an acceptor of hydrogen bond, but we have found that in case of thiols, it is not the case. And the main objective of the study is actually whether sulfur and hydrogen bond can be formed with water, or whether sulfur can act as a donor and oxygen can act as an acceptor, in contrary to that of the other cases, and whether is there any binding energy of complexes of aliphatic, what will be the binding energy of the complexes of aliphatic aromatic thiols. As I told you, this paper is published recently in Journal of Molecular Liquids, is accepted just to one week back, and this is the title of the paper, Evidences for Sulfur-Centered Hydrogen Bond with Sulfur Atoms as Donor, Aromatic and Aliphatic Thiols in Aqueous Solution. The aliphatic thiol is actually methane thiol, it is ethane thiol, it is propane thiol and benezyl thiol, and this is the optimized structure geometry of the thiol complexes. And we use the B3LYP D3 for dispersion correction by using CCPBT as a level of theory. It's the aromatic thiols we use. These are the thiol, simple phenol thiophenol. Next one is the parachlorothiophenol, and next one is the 4-cyano-phenol, and this one is the phenitrophenol. Okay, and we consider only the para-isomer because to avoid the steric repulsion possibility in the ortho-isomer. And all studies are done by using OCA, as I told you before, and also the multiple differential method is used for AM analysis, and for NPO, Gaussian is used. Okay, we make use of geometry optimization and B3LYP D3BJ method, and also domain-based local pair natural orbital coupled cluster theory is actually considered to be a very good version of the ab initio theory. Is used in a small approximation only, but gives better results. And we made use of local energy decomposition by using OCA in the same level, DLPNA level, and QTAM analysis. And again, it's a basic theoretical background of LED in which the interaction energy we can decompose into two. One is the propulsion energy for the geometry to form the complex, as internal energy, internalization or interacting energy. And again, the propulsion energy can be used actually for several purposes, and this energy is used to distort the original fragments of X and Y to make the complex. And a delta E internal energy can be decomposed to different parameters for reference internal energy and the correlation contribution. And you can see that the second in the reference energy again can be divided into electrostatic preparation energy, electrostatic energy, and also exchange energy. And you can see that the exchange correlation energy, we can use the strong field is there and also weak force is there, and there will be triple correction is also there, but we are not considering triple correction here. Is the results that you obtain, you can see that in all the cases you found that there is electrostatic interactive force is there, it's having negative energy, and so this indicates that there is a definite formation of complex within thiols and aromatic and aliphatic thiols and water. And you can see, very interesting to see that rather than the aliphatic thiols, aromatic thiols shows better interaction, and also there is exchange effects, and also there will be correlation effects also is there. Okay, and the electrostatic effects and exchange effects and the correlation effects, and you can see them together. And these three effects are responsible for the interaction between the water and the within thiol, where thiol acts as a donor and the water acts as an acceptor. But in, as I told you before, in most of the cases, water acts as a donor, not as an acceptor. So the binding energy in all the 6 systems are very good. And also the total binding energy is not just the strength of the hydrogen bond, but it's actually a measure of the strong interaction energy between thiol molecules and water molecules. And also there's dispersion interactions also there, and that is why we got the correction for the interaction energy is there. And the interaction energy for thiols with benzene rings, thiophenols, and benzyl thiols are much higher than that of the competitive thiols containing benzene ring. And the aromatic thiols, we have seen substitute thiophenols have greater interaction than thiophenol water system. Among the substitute thiophenols, chlorothiophenol and water system is observed to have the highest interaction. And the LED terms of decomposition, the reference energy and correlation energy is reported in that paper. And also we have seen the electronic preparation energy, the energy required for molecules to be geometry where they can be interact because repulsive interaction. And the electronic preparation energy counters a strong electrostatic interaction between the molecules. We confirmed that by using quantum theory of atoms and molecules approach, where we measure the Laplacian electron density, del square rho is more than 0 for the ratio of kinetic and potential energy. The gradient of kinetic and potential energy is more than less than 1, shows more than 1 shows the interactions are of no covalent nature. It's not covalent bond in fact formed between the water and thiol molecules, but it's definitely there is non-covalent interactions like hydrogen bond reaction or the van der Waals or electrostatic forces of reaction. With the QTM picture in medium thiol, there is only one bond critical point between this water and this hydrogen atom. But in the case of the other systems, there are 2 interactions possible. There's the terminal CH or the other CH interaction can also interact with the oxygen atom. Here thiol is interacting, but the O is also interacting. In other cases, in the aromatic thiols also, there is hydrogen atoms. Here's chlorine is also interacting, and again, sorry, here is thiol interaction, and this is the hydrogen interaction is also there. In all the aromatic system also thiol interaction is there. And here seen that this is the energy that will shows the binding energy of the bonds. We can see that our SHO, look in the SHO data, you can see that always SHO data is higher in the case of aliphatic thiols, than in the aromatic thiols than the aliphatic thiols. Okay, and the natural bond orbital analysis is also used for actually the interaction. The study, we have seen that there is electron delocalization can be measured by using natural bond orbital analysis. We use this facility available in the Gaussian Norton software for doing the natural orbital analysis. There it measures the delocalization of the electrons from the lone pairs of actually water to that of the hydrogen. And you have seen report we can see that there's a good interaction in a orbital interaction between that of the lone pair and the SH bond is there. Lone pair and the antibonding orbital of the SH bond. You can see that this is the different types of interaction energy, but we can see that always the delocalization is heavier in the case of aromatic systems than that in the aliphatic systems. And to conclude, I would like to conclude the study like that it's a theoretical nature of the hydrogen bond between aliphatic and aromatic. That was the first reported by us. And in the hydrogen bond involving oxygen sulfur atoms, generally the oxygen atom is a donor and sulfur atom is the acceptor. But in this case, sulfur atom acts as the donor, respect than being the less serotonegative atom. And the LED analysis, AM analysis, NBO analysis, and the FMO approach studies proves the sulfur centered hydrogen bond. It's all about my research. And I'd like to tell you the importance of solvation science in the recent developments, development. You can see that's why solvation science is very important. European Union, Germany, Swiss governments have a combined project called the Cluster of Excellence in Solvation Science. They pumped a lot of money to study solvation sciences, and they study local solvent, dynamic solvent, stress solvent, and they also have a method called solvent study called solvent shaping, and the solute impact on the solvation contribution also is analyzed. And it's a very important area, and I think the physicists may also consider the effect of solvent also while doing some studies in solution. Now I am personally now working in a program where I am studying the effect of solvation on the molecules with internal cavity. And normally the implicit solvation model ignores this cavity. And I am nowadays designing an experiment, or we are modifying the solution model such that it could also account for the internal cavity of the system also. The porphyrin, corals, and amethyrin and phthalocyanine systems also have got this problem. This is the implicit solvation sphere, and this is the explicit solvation. We're going to see how it will correlate with each other. And let me thank for my part of acknowledgement. I thank my dear family and also my good friend G. Vijaykumar, who unfortunately passed around 2 years back, and Professor C. Johan Panikkar of the University of Kerala is one of my good friend and advisor, and my 2 postdoc fellows, Dr. Tipuyendran and Ilangovan. They're nice fellows, and I have an exchange student from the University of Gashon called Subedja, and I got to post my PhD students and my collaborators, Ralph Puster from Germany, which work on soft proton sponges, and Steven Amako, we do on molecular dynamics. Penny Govind also work with molecular dynamics, and I am very much thankful to the Royal Chemical Society for the research grant fund award given to me recently. I thank you very much. This is my email address. If you have got any clarification, clarifications, you can ask at any point of time. Now, if you have got questions, you can ask me. Thank you very much.
Okay. Thank you, Dr. Thomas. And before we wind up, if there is any comments and queries, please go ahead. Anyone?
Hello. Yeah, I have a question. It's me, Dr. Rai.
Yes, Dibya.
First of all, I would like to congratulate you for being the top 2 scientists of the world, in the list of top 2 scientists of the world. We forgot to mention that one.
Yeah, no problem. It is you.
Many congratulations, and we are very proud you are here and you deliver a very nice talk. Sir, I have a question regarding you just saw a table where you said that basis set, the order of the basis set is increasing somewhere.
Yeah, I know. You can ask. I know. I understand. I understand.
Yeah. And my question is there, is there any way that we could choose the proper basis set, like before going for a trial and error basis?
Yeah, actually, these basis sets are generally considered. We need more and more good basis sets because there are some faults with the existing basis sets. So every day, people are coming with new basis sets because they have identified some problem. Okay, and we have to follow the basic primary literature available, and also we have to look into the benchmarking benchmarking papers, then only we can understand which solvents, which basis to be used. And actually, it's a main problem with me also, because we can't predict, we cannot generalize which basis to be used for a particular study. And so what I do is that, and I normally benchmark the systems, because I may look for always a experimental data. I always look for an experimental data from a system. I try to correlate some. I'll try with different bases and different functionals, and I'll try to at least get some correlation to at least one experimental data, like a bond length or some bond angle or some vibration spectra like that. Then only we can say that this basis is good for that system. There's no golden rule to select a basis set. Okay, we have to use always trial and error method. There's no other way for that. There's a major problem.
Is there any, I mean, the average type of basis set, like which will not consume more, I mean, this thing, memory computation, I mean, which is, I mean, in, you know, like which will have an average work in computation as well as giving the, I mean, more or less accurate results?
Yeah, actually, for me personally, I like the basis set CCPVD set. This is a Dunning's correlation consistent CCPVD set method. I don't put augmentation, but I'll put the CCPVD. I am fan of that because it is very good effective method for as far as I am considered. It's a good method. Okay, and also okay, I can use Aldrich method. I use DF2 T set VP. That's also good. That's also good. But I don't know whether if you look for a periodic system, like when you look for in a physics point of view, maybe sometimes those messages will be bit expensive because it will take a lot of time. For me, I am working only with one molecule. That means I can account for, I can at least spare some of my computation time for that. But maybe for physics people, I don't know whether you can afford that too much unless you got a good computational power.
Yeah, I think in physics, I think we don't have much choices because we are using like SP, like
very small base.
Single this one, this polarization and this double zeta polarization.
Yeah, they are actually low as far as the molecule considered. They are not that much good. We can afford more. In chemistry, we can afford more, but in physics, we can't afford that.
Thank you.
Thank you.
Okay, so is there any more questions? If not, then let us thank Dr. Thomas for his elaborate presentation, and hope it definitely will benefit the participants. So with this, let us conclude this session, and yeah, we will have this special talk later at at 6:30, I think. And so with that, again, I thank you, Dr. Thomas, for your elaborate speech. So
thank you very much. Thank you all.
With this, we conclude the session.
So a few words from the organizers. Please join us for the special talk, which is scheduled at 6:30. The link is there in the chat box. So we thank everyone, the participants, as well as all the speakers in today's session. Thank you.